Co-chairperson, Dr. Suman Manager. We have five keynote lectures in this session by different distinguished professionals in their respective profession. Our first keynote lecture will be by Professor Dennis Bragado. I don't think he needs any introduction, but as a formality, I'll give you a brief biodata. Professor Bragado, he got his BS in Civil Engineering degree from MSU in 1974. That's in Philippines, right? Then he got his Master's in Civil Engineering from Asian Institute of Technology in 1976 and his PhD in Civil Engineering from Utah State University, USA in 1982. Subsequently, he branched out to ground improvement and geosynthetics after he joined his research career. He has 2 books, 7 chapters in books, 22 edited books, 5 guest editorship in journals, 157 journal articles, 311 conference invited papers, 81 keynote lectures, and he also advised 17 doctoral students and 160 master's students. He has also 2,329 Scopus Science citations. He is a geotechnical specialist right now at Blue Line Extension of Mass Rapid Transit Project in Bangkok, as well as freelance geotechnical consultant in Southeast Asia region. I'd like to invite now Professor Bragado for his keynote presentation.
In my book on soil improvement, put together depending on what type of soil. If it is coarse grain, then we have here is working in the soil only add force, vibration. So we have dynamic compaction and vibroplotation. When it is fine grain, we have drainage. So we have vertical drains, vacuum drains. If it is, we add soil, material other than soil, we have reinforcement for granular soils, and for fine grain soils, we have chemical cement stabilization. When you look at Bangkok clay, we have techniques from 10 to 20 meters, quite uniform, about 200 by 400 kilometers in the central plain of Thailand. And when I entered into this research, ground improvement, in 1982, there were already research before me at the know-how, or the Cobra zone, which is now the Suvarnabhumi Airport. And the highest embankment they can construct without improvement is 3.4 meters. But before me, there were some works that has been done on drainage, and particularly this one using a sand drain. And they don't find any difference between S with sand drain and no sand drains. This is because the field is too low. It did not exceed the maximum pass pressure. So in anything reloading with soft clay, you have to exceed maximum pass pressure to have meaningful compression, and the maximum pass pressure here. This is the overburden pressure, maximum pass pressure, and the surcharge. The surcharge should exceed the maximum pass pressure. And then we have the sand wicks at the Pumpracho Royal Thai Navy. And in this case, sand wicks is like packed drain, where you have the tube, geosynthetic tube, fill up with sand and bring it to the field and push it down. It's displacement type. And then the loading was too low. Then they found the mistake, and so they add more height, and they found some separation between with these sand wicks and without sand wicks. The problem here is the slow construction and the displacement type of installation. So there is some there is some problem when you push the drain. There is kind of a disturbance. The larger the diameter, like sand rain, the disturbance is also greater, twice as much. So this has been experimented a lot. So the PBD, which is smaller, has advantage, smaller diameter, has advantage because of smaller diameter and smaller smear zone. And then there was an experiment at the Suvarnabhumi airport site, 1983. I just arrived at the time. And they have the 26 centimeter diameter, 14 meters long, sand drains, which is jetted to prevent disturbance around the sand drains. But they found some hydraulic connection in the subsiding ground. Because of the drain, it made the subsidence faster. And that made a hindrance of the use of the drain. Like to illustrate later that, see, this is the jetted sand drains here to prevent disturbance around the sand drain. And if you have the displacement sand drain, there is disturbance. If you have the sand wicks or packed drain, there is disturbance, it's displacement type. And this is the PBD, smaller disturbance. And you can imagine making these jetted sand drains a lot of time to construct. And it's also a sand drain. So that hydraulic connection, subsiding ground, they say the PBD drains cannot be used in subsiding ground of Bangkok. So I make my own experiments at the campus of the Asian Institute of Technology, and using a smaller mandrel size and a bigger mandrel, two embankments side by side. At the time, there's a lot of space in the campus to do this kind of full-scale experiments. And we found that there is improvement. This is the soil profile, the properties. This is a smaller mandrel and large mandrel. The smaller mandrel is higher, faster than the bigger mandrel because of the less disturbance, depending on the mandrel size. So we need to reconfirm the smear effect. When I came in 1986, they never mentioned about smear or disturbance. But we found that no smear, over-predicting settlement with time. At the same time, Rixner published paper, publication, that because the drain is here, surrounded by the mandrel, there is disturbance equivalent to twice as much the size of the mandrel. And that starts research on the smear effect. So there was a competition for the second Bangkok airport. The NGI, Norwegian Geotechnical Institute, proposed this cost that VBD is the cheapest, followed by the sand compaction pile, deep cement mixing, and concrete pile. And there were proposals to support the runway, concrete runway by concrete pile. But it is a subsiding ground. So if you have a concrete pile, the runway will be not moving, no compression, but the surrounding ground will settle. And they made competition for this alternative. And we won the competition and get the project. Sorry, there is some problem with the computer, but it's going on. So this is what we did. We did some experiments in soft Bangkok clay, and the project was very successful. And we found no hydraulic connection because we have only PBD on the soft clay. Below the soft clay is medium clay, below the medium clay is a stiff clay, and then the dense sand. Sand is an aquifer with drawdown condition because people pump water from the sand. But when you put 14 meters, we use only 10 meters here for the PBD. So that was successful. This is the reason why there is hydraulic connection in the subsiding ground. Instead of the isometric pressures here, there is under pressure due to the pumping water from the sand. And so water from the clay is draining to the sand, compressing the soft clay eventually, slowly. So we put the drain only here, 10 meters. We did our experiment at 20 meters. So for soft ground, because you have a lot of voids, this was solids. Solid is dark, and the voids is full of water. The only way to improve is take out the water, dewatering. And if you have the conventional preloading, it takes a long time because of the drainage path is too long. So you put artificial drainage paths, that is the PBDs. So the drainage path will be between PBDs, which is quite shorter, so we have faster consolidation, rate of consolidation. So these drains are installed at one location per minute, about 10,000 meters per day. And it's just modified back home because we have only 10, 12 meters deep. The PBD is made of geotextile. The core is made of channels of flow, while the jacket is filter that minimize the entry of fine particles. And this drain can deform when it's compressed, about 10% compression. And when it deforms, the discharge capacity decreases up to only 20%. But that's all right, because the maximum here 2,500 meter cube per day, 20% of that, we still have 500 meter cube per day. The discharge is not a factor here. As I mentioned, this is a comparison of the previous sand drain versus the PBD. So the disturbance around the drain is called the smear zone or smear effect. Is a barrier to the drainage of water to the PBD, which discharges here, called vertical discharge capacity. So a lot of research was done to minimize this smear zone. And we found that the smear zone size is size of the mandrel, DM, and permeability of the smear zone, KS, ratio with KH, the original horizontal permeability. KH over KS is a measure of the smear zone, smear effect. And we found those values in all over in different kinds of clays. So in the Suvarnabhumi Airport, there is a west runway and east runway now operating. These are on vertical drains. The third runway is under construction. And some areas here we use vacuum preloading. And this is the area of the Suvarnabhumi Airport. The old airport here is Don Airport. So this is our experiment. We put in 12 meters of vertical drain, 4.2 meters high surcharge, which exceed the maximum pass pressure. There are 3 test embankments, TS1, 2, and 3, and different spacing. You see the closer spacing have faster rate of settlement than the higher spacing. The spacing from 1 meter, 1.2, and 1.5. So the question was, is it effective? We found that the water content reduced from the original after 1 year. Then after 2 years, you can see the blue one. This is the water content profile with depth, reducing the water content. And since it is a soft clay, when you reduce water content, the shear strength increasing up to 2 times after 2 years. So that is now the successful implementation of PVDs. At the time, the people realized, oh, PVDs are working. So then they start using PVDs. So the prefabricated vertical drain company should give me a royalty so that I restore the confidence on a subsiding ground. If we can only improve the soft clay, it's working, and it's the cheapest. So now we found 2 back-calculate parameters we need. KS over KS, measure of smear. DS over DW, the size of the smear. QW is the discharge. And we can get the CS value, very important for design, the coefficient of horizontal consolidation. And this is the result of $1 million research grants, KS over KS, CH, DS over DN, QW, and CH at different discharge because we have different spacing. But now there was a project by the Department of Highways. And this is the ring road, outer ring road. Now it's working well from Bangkok to Pattaya, passing by the Suvarnabhumi Airport. There was a budget for doing a test embankment. However, there was a cancellation of that budget. So they construct this embankment and specify that the highest height is 2.7 meters. But theoretically, you should go up to 4 meters and then allow settlement. And then you should go to 2.7. But this was not done. So it's settled. Now the embankment height is, some are 1 meter or less. But there is uniform settlement because you have equal spacing of PVDs. You cannot see any cracks in this road, and it's working well. The only thing is they have some flood walls along it, so it will not flood during extreme rain. And then the advent of vacuum preloading. We add atmospheric pressure to the normal surcharge. Our first trying was, there was a field study that we have the PVDs, the tube, to the vacuum pump, but they are not connected to each other. And we put the geomembrane seal. This is a vacuum pump. Goes here, we have the vacuum meter or pressure meter. And we found that the pressure at 60 kPa here at the top, 90 kPa at the pump, is only minus 15 here, and the other environment only minus 25. There is inefficient transfer because there is no direct connection between PVD and the tube. And you see our settlement here, this is the actual. Professor Chai make a model, the actual, and then with high pressure and no vacuum, see we are only halfway. So when we compare with our conventional surcharge at Sonapum, you see this conventional surcharge, it takes about a year. And this is vacuum. Because the loading, the pressure is quite low, we have only half the maximum compression. So actually we were not happy with the result. And this was done by a company from Malaysia. And we only published this in Southeast Asian Geotechnical Conference journal. But another professor made a big, he made a paper that this is successful. Anyway, that's the story. So it make a mistake. So now what's going on? There is a direct connection of the drain to the vacuum pump. The other one is there is a membrane, but also a direct connection of the PVD to the tube. So this is the PVD here with a horizontal drain connect to the tube that goes to vacuum, or wrap around the whole PVD to the perforated tube. And this is the best in Ho Chi Minh, in Vietnam. The one when you have membrane, there is some reduction of the vacuum. But this one you can see 60 is maintained. So this is the best way of making vacuum. You put direct connection with PVD and then cover with membrane seal. And you see the membrane seal here. So before my retirement, I have a student doing heating of the clay. And you can see here that we have the model test. We put in the middle of PVD some special heater wire. And we found that when we heat the clay, the permeability increasing up to 3 times. Why? Because the viscosity of water reduced. And also heating the clay expand the pore water between the clay solid particles, and the excess pore pressure can be drained out easily by PVD. So we have this experiment, and we found PVD only, vacuum PVD, settlement with time, thermal PVD. Now this is the secondary compression, already erased. Thermal vacuum combination. And you can see the CS value increasing, the KS over KS, almost 1.1. So, mean 10% only remaining for the smear zone. So, this here with thermal PVD 1.4, 40% remaining. And then when we have the optimum mixing, cement mixing, we found optimum cement content here, and the cement content is optimum mixture is with liquid limit. The liquid limit to clay is a good mixing. This is mechanical mixing, jet grouting. We use it to support reinforced embankment, and use hexagonal grit as reinforcement. And compare it without improvements using steel grits. You can see the difference here. Compression is more for without improvements. The mixing one, we have these different kind of patterns of deep cement mixing. The pile type and the wall type, the pile type has more lateral movement. And if we use it to support excavation, we have to put layers of PVD, of deep mixing pile here, layers to support excavation here. Or this kind of supporting the excavation, we need a lot of this method to prevent failure. Because shear failure and flexural strength is low for the deep mixing pile. But there was a canal, drainage canal from Sonopom Airport to the sea. Here is pile type, wall type, and this is the canal. And this canal here, from the airport to the sea, and you can see failures. Failures, why? Because the number of the piles not enough. So we need to add more piles. Then we also experiment the steepened deep cement mixing, inserting RC pile in the middle to increase axial compression resistance. Its DCM is larger than the DCM. Lateral is DCM larger than DCM. So with that, we can improve the support, vertical and lateral. Then we go to the earth reinforcement. And this is this embankment. Here is metal, steel bricks, and metallic strip. This is geosynthetic, SDPE, and polypropylene and polyester grids. You see, this is geogrids, metallic grids. This is much stronger than the geogrids. But we put in at the same vertical spacing. These metallic grids, no problem, but the geogrids move laterally. Even though it's sloping a little bit, this is the metallic, vertical, this is sloping for geogrid, but it moved because the vertical spacing were the same and the strength are different. We also experiment using rubber tire chips mixed with selfie sand to make it a lightweight fill. And it's construct this embankment. You see the tire chips mixed with sand and this embankment and settlement. You see settlement is lower than the conventional one. We have also some tests with vertical facing using steel grids. And this is the construction using precast concrete facing. You see this is very convenient, there is no bracing, and then finished product. I want to go and I want to emphasize that when you construct a wall, drainage is very important. This drainage soil here with a tube must be done properly. Like what we have here. We have drainage layer wrapped around by geotextile. And this was failure in Penang. I think Professor Kausya knows about this. There's a lot of water coming through here. Failed the MAC here. And if you like, you have to provide a lot of drainage. Then we go to the rainfall-induced failure because of the shallow ground rock, parent rock here. So it has artificial groundwater. And this is part of my experiment when I was young in north of Thailand. You see here, this is, I look at the different zones of weathering of granite. So this is called granite residual soil. What happened? Because there's a lot of failure here because the water cannot penetrate through and it encourages failure in the surface. So this is now it's a repair of the highway department project I don't want to, I want to skip this because my time is up. Just want to go to the last topic. This is a failure along the road, in the road near China from Laos. And this failure, we use gabions here and geotextile reinforcements. You see the gabions along the river. And the road is here. We have to remove the loose material going up to 30 meters. And 1 year later, 5 years later. And this is at the Mekong River. There are two ways of doing revetments. And this is the Mekong River revetments. We use a combination of gabions and benching type gabions and mattresses. This is one other area where we have the benching type. And the last part here is a project in the south of Laos, ATB project, erosion, dissolve, outer curve, inner curve. And our solution is gabions with mattresses, reinforcement. The reinforcement is only for infinite slope, because there is some, the infinite slope is the lowest factor of safety. The failure plane is parallel to the slope plane. So we have to analyze stability and then construct the gabions here. You have to put geotextile filtration between the fill and the gabions, and construct the facing by geobags. This geotextile geobag. Geobags is good in constructing the reinforced slope. It's very fast. So we have gabions. This one now is the mattress, 5 big stones. This river go up to the top during rainy season. It floods the area. And you can see the bags here. Then you put the wrap around facing for the bags, and then dewatering using 2 piles of steel sheet pipe, 2 rows of steel sheet pipe, starting with the gabion and then going up with the mattress and the textile reinforcement. Thank you very much. Historical and pre-historical earthquake in this region. And before starting that, in Nepal, here is Nepal. These red symbols are size of the symbols are a bit greater than 8. This one and between 6 and 7. And these are all red one are the all instrumental earthquake in this region, and yellow one are the historical earthquake. And I have collected these from different catalogs. Sources are in different catalogs. What I am emphasizing here is the more than 50 million people are residing in the Ganges basin, and we have this big earthquake in the head of this population. So knowing the impending risks from this source is very essential to understand, to evaluate, to mitigate the seismic risk in this region. So now I would like to highlight a little bit of historical earthquake in this region. I go back to 1223. I go to 1223. It is just mentioned in a chronicle, that many people died. We don't know how many people, and we don't know what happened during the earthquake. Just it was mentioned in a chronicles, Vamsavali, Gopal Vamsavali. A lot of damage and resident buildings and temples. Then we have big earthquake of 7 June 1255. This is the most devastated historical earthquake in this region, where the king of Himalayan was died, and you have a lot of earthquakes in many days after the earthquake. Also many aftershocks, and 1/3 population of Kathmandu was vanished. So I presume that this was very big earthquake, but still we don't have any report of the damage. Only the damage as reported around the Kathmandu, not either side of the Kathmandu. So it is very difficult for us to locate the epicenter and zone
of this earthquake event. So we have 1344, we have one earthquake, and here king was died next day of the earthquake, not same day. In 1344, king was died next day of the earthquake. So the king was Arimalla in their pattern. And there are other very scattered reports of the earthquake, 1408, many people died, nothing only mentioned, 1681, 1767, June 4th, 1808, several people and animals perished, houses collapsed, only written that. I am quoting this from different paper. And then next one is 1833. Which earthquake I believe is the return of the 1215 earthquake in the same source and the same area. So this earthquake was 7.7 magnitude, but it was similar to 7.8 magnitude of the 2015 Gorkha earthquake. Location was nearby Tirsuli, and north of Tirsuli means today we have the equipment to detect. Today we have the equipment to measure the seismicity. We can locate precisely. But at that time, people put the epicenter where is the maximum damage. Now also, if you think of 2015 Gorkha earthquake, if there was no seismometer to be recorded and there is nothing to record it, I will put epicenter near Sindhupal or Nuwakot or north of that. So I presume it was the same case. And if you are interested in this article, you can look in the Cornell. There was one Cornell was living in Kathmandu. He was writing his diary every day what happened during the 1833 earthquake. So I took this from his account. Bhaktapur and Patan in the valley and adjoining Banepa, a lot of 80,000 buildings were collapsed. And then came 1866, south of Kathmandu. After 1833, there was an earthquake of 1866, 23rd of May. So a significant portion of Kathmandu was destroyed with magnitude around 7. They have mentioned this magnitude by the damage pattern. And over 200 shocks were felt up to Ganga's basin and even in Darjeeling. It is written there, shocks were felt there. Then everybody knows this earthquake, 1934 earthquake, estimated magnitude 8.3 and 81,000 completely destroyed, the 20 maximum intensity 10, 55,000 building affected in and 12,000 are completely destroyed. This is the account of 1934. Now 1936, we don't have very good record, but we still have the feeling of earthquakes. 1988, I forgot here one thing, 1980, Bajang earthquake in western Nepal, and 130 people were died. The magnitude was 6.5. And then 1988, magnitude 6.5 epicenter in Udaipur district, 720 people were died, and 66,322 building collapsed or seriously damaged. And 1993 in Jadarkot, it was not very big, some building were collapsed. And I forgot here one earthquake, 1997 in Jammu, in near Rasua earthquake. There many houses are collapsed in the Dhunche and the Tirsuli area. And 2015, epicenter Barpak of Gorkha districts, and more than 900 people died and many houses are destroyed. These are the account I put for the historical earthquake. What is the problem that we have now is source historical earthquake for past earthquake problem we don't have record. If you want to source historical earthquake, but we have no record, records are lost. And excavate the frontal thrust, I will tell you later. Because the earthquake changed the morphology of the frontal fault, so we want to try to trenching in the frontal fault, but earthquake that occurred in the past 10,000 years, problem many earthquakes have no surface rupture. Like 2015 Gorkha earthquake, many earthquakes doesn't have the surface rupture. So we cannot precisely, accurately find out the return period of the earthquake. So there are problems. Some earthquake doesn't reach to the surface. And next is search for the evidence for repeated liquefaction in the valley. Problem is magnitude or casual earthquake. So liquefaction, what is the baseline to make a liquefaction? Might happen sometimes, it depends upon the size. of the earthquake. We cannot say looking at the liquefaction precisely magnitude and timing. So dead synchronous historical landslides could be rare. You cannot separate, if it's a landslide, but you cannot separate whether it was triggered by rain or triggered by landslide. These are some very difficult issues. Computer model depends on the assumptions, what we assume that may give you the result. So these are the things very difficult to make the seismic risks in the, to evaluate the seismic risks in the country. So two important goals. Then we started to find the two important things. Okay, we don't have history, and even 1255 earthquake doesn't have where was it? We don't know the epicenter. So we started to see whether how many earthquakes reach to the surface at the base of the Himalaya frontal thrust. So to work with this one, we put two things. One, identify the surface rupture of the great earthquake. Now I finished the historical part. Now I am going to prehistoric, how to find the prehistoric earthquake. So characterize their sources and return times over multiple cycles. So these are the two important goals we are working. Especially I am working on it. Then, first of all, we want to know what is the model. Model is this. This is the 3,500 meter contour. This is 3,500 meter contour. This is the white one. This, all the microseismicity of the Nepal, of the Himalayan region is concentrated with a narrow belt around 3,500 meter contour, which is at the 15 to 25 kilometers in the depth of in the front of the higher Himalaya. So this is the model. This is where I am talking. All the earthquakes are nucleated here, either 1905 Kangra earthquake, 1934 Bihar Nepal earthquake, 1897 Shillong earthquake, 1950 Assam earthquake, whatever, all are nucleated in this region. And if the earthquake is very big, this is the frontal thrust, most active frontal thrust of the Himalaya. This one, the MFT. This earthquake rupture goes all the way to MFT. And if earthquake is like a 2015 Gorkha earthquake, it stops like below Kathmandu in case of 2015 Gorkha earthquake. It stops here and it does not reach to the surface. So in my talks, I want to focus what is happening here. How many earthquakes reaches in the MFT in the past, in the prehistorical time. Why we are looking at this part? Because this is the seismotectonic model of the Himalaya, because the convergence between Indian plate and the Tibetan plate is happening here at depth, and the surface expression is here. It is doing this. MFT is here, but the collision is going on. That's why we have this intense microseismicity here, because stress is building up there. That is why we have very intense microseismicity there. With this model in mind, we started to look at the known study. Means 1934 earthquake was happened in the north of Tumlingtar, Shamgosaba. 1934 earthquake, the rupture, we presumed will be here. So we targeted our focus to find the rupture of the 1934 earthquake in this part. And similarly, so these are the few points in the 1934 intensity zone. I look for the geomorphology, I look for the ground truth to find the historical earthquake, prehistorical earthquake. Then I show all the time this picture because I like this picture, because the Himalaya collision, when you have earthquake, then it pushes towards south. Every time it pushes towards south because stress is developing from south, and when you have earthquake, then it goes back of the elastic energy. Then what happened here? You see, this is the Shivalik rock. These rocks, when there is earthquake, these fluvial sediment, these are the fluvial sediment, are dragged and ridden over it. And these two layers were together before an earthquake, and they are shifted, and we have confirmed with the dating of from the charcoal dating. These are the, you can see other fault also in this part. You can see other fault also. So with this, we found at least 2 earthquakes here. One is 1255 and another one is 1934. So we can tentatively think of return period of the mega earthquake, 8 plus earthquake around 600 years plus minus. So these are the some fault. I am sorry, these are some fault coming to the surface. So there is some challenge with the paleoseismology also we cannot do. When there are so many large processional throw, one earthquake has a throw of 20 meter, sometime 20 meter, sometime at least 10-12 meter throw, and 5 meter of the vertical separation. So digging 2 trenches is impossible. Digging very deep trench, because if you want to know 2 earthquakes, you have to dig more than 10 meter. It is very difficult and it is very unsafe. So there is some limit of finding multiple events in a single trench. So because of intense monsoon, signature of the earthquake are erased rapidly. Even in 2-3 years, 4 years, if you go to Sichuan earthquake now, you don't see any evidence where there is a fantastic rupture in the 2008 Sichuan earthquake. So similarly in Nepal, you can imagine if you are looking at the rupture of 1934 past earthquake now, you have to be very careful. You have to work on a micro topography rather than this present topographical map of the 25-10 meter contour. It is very difficult. So rapid urbanization. If you see MFT, now rapid urbanization. If you see Bardivas, where the fault emerges at the surface, there is a rapid urbanization. Now everything is modified, so you cannot work there. So dense forest, because when there was an earthquake of 1934, due to malaria, nobody was living in the frontal part. In Surya, south of Surya, nobody is living there, so nobody has reported what happened in the morphology in the front. So we don't have any visual record of the also of the rupture. So in terraces, then what we think now? What we think now is, now we look at the terraces now. We believe that terraces are a good marker. They are uplifted by earthquake. So we are trying to look the terraces, dating the surface, because when you have a river, then you have erosion, then you have earthquake, then what I have tried to explain the model, then things are uplifted. Then they started to erode again. Then you have another earthquake, you have another uplift of 4-5 meter. So there is a systematic terrace distribution on either side of the river. Then we date those terraces and we find some idea of the return period of the great earthquake. That was the, and mapping. So mapping the terraces, we start the LIDAR mapping, airborne LIDAR. So because airborne LIDAR, what airborne LIDAR does, it cut out all the trees effect also. Because even you look the aerial photograph, you cannot find all the terraces because they are covered by dense forest. So in this area we started to fly and to map the terraces. So covered area 1000 square kilometer, total points 9 billion points. So we are sampling 4 points per square meter. Per square meter we are sampling 4 points. So population density, point density was 3 to 6 points per square meter. High resolution bare earth terrain model, and 6 GPS stations were installed to serve the base station. Base airport was Viratnagar. While we are doing this survey, and so the results are here. Some results are here. You see, these are terraces. You know, there are terraces. One terrace is here, another terrace is here. You have to see the flight of the terraces around. So you go there, you date those terraces, you dig pit in these terraces. So many terraces here, and so this is the This is the total composite map, so you can zoom anywhere where you want and make your DM of 20 centimeter resolution. So you can find all the contour, and you can see the micro topography also, or if there is some fossil topography by earthquake. So only solution in the Himalaya, in the frontal part, in the Himalaya to see the past earthquake is LIDAR. With the classical topographical mapping, we could not solve the problem. So look at this picture. I am showing one example. Okay, let's go in. Okay, look, these are the river. This is the river. You don't see any terraces here, and then we map by LIDAR, and still you have this part. Every part is like this. This is the forest. Then we cut all the forest. Then what we saw is we cut all the forest. What we saw is this very nice surface terrace. Before I worked there 6 years, looking at the aerial photograph, it was very difficult for me to find this surface. So it is very useful tools. Then we took a profile. Then we took a profile on it. Then we found some base height of all the where from Bagmati, at least from Bagmati to Kosi, there is one ultimate height 40 meter. Every river you have these terraces. Yeah, these terraces you have it everywhere. Everywhere you have from the river level you have one river just uplifted by 6 meter. Very close. The close terrace is uplifted by 6 meter, then 12 meter, then 18 meter, then 24 meter around. There is a very fantastic classical level of the terraces, and you date them, and six event of magnitude 8 plus with the since 4000 BP. Since 4000 year BP before present, there was 6 magnitude 8 plus earthquake in that region with the elapsed time of 600 to 700. What we found from this study. We have the same height of terrace. I don't have time to show all these figures, so I gave you one example. Now I will give you a little bit of how it works. Everywhere you have the one height in that between around 10 kilometer from MFT to the north, 10 kilometer from MF to the north. You have a systematic terraces distribution, 40 meter from the present river bed, and systematically uplifted by at least 7 level of terrace, 5 to 7 level of terraces. This is what we found. You see. So with all this, what we came to know is in this area, maybe next one is better. Okay. In this area, what we found is, you see, we found 3 to 4 more events here. We date the surface 1934, 1255, and one more surface 50 in the trenches. We found these 3 layers of the 3 episodes of the earthquake, which separated by at least by 600 to 700 years. So this is the model we developed from there. Oh, sorry, I am going. Okay, this is the final. What we learn is this is the historical earthquake in this region. So you see here, 1934 is 1255. We believe it's the same written. 1255 was written of the 1934 earthquake, and similarly 1833 and 2015 they are conjugate earthquake. They are repeated. So in this part earthquake return time is 200 years, 185 years. If you see it in 1833, 2015, 178 years, and we don't have another earthquake here. We don't have from 1505. Even in the trends, we could not trace another earthquake because it's very old earthquake. So to find another old earthquake, it takes, we have to excavate more. So still we are working in this. So right now we are focusing this area, and because in central and eastern Nepal, central eastern Nepal and central Nepal, we know little bit of return time, but here we still have working on it, whether 1505 earthquake, maybe big area and more time, or we lose some earthquakes, we don't know. So we have still, so we are only saying this is a big seismic gap, next is waiting, all we are talking, but actually we don't know what is happening there, and whether there is a length of the rupture might be hundreds of kilometers, 500 of kilometers, so that it takes a long time to saturate, or there is some way to have a seismic creeping or something like that in that region. We don't know that. Still we don't know that. So I already put these things in my slide. In Kathmandu region, 2015 earthquake, then 1833, 1600. So there is some systematic, you see, there is some systematic distribution of 1400 and 1200. So there is some systematic frequency of the earthquake elapsing in 200 years in central Nepal, but we could not develop same sort of model in either way. Here we have 1255 and 1934, but here we still don't have 1505. What was the penultimate earthquake or previous earthquake? This zone, we don't know it. We believe from our research, in one article we published one article, 1344 earthquake was around Pokhara and it reaches to the surface. Now this part, we propose this 1, 2, 3, 4, 5 zone. One big zone is western Nepal, then central western Nepal, Pokhara region, then Kathmandu region, then eastern Nepal. These are the model we think from our study. So, what is happening here is, okay, along 70 kilometers of the MFT in eastern Nepal, where we are, our LIDAR measurement implies that up to 7 magnitude 8+ earthquake produce 6 to 8.3 meter of the repeated characteristic processing throw. One earthquake 6.3 meter of the 6 to 8 meter of the processing throw, and this paleoseismic record extends back to 4,500 years BP, with the pluvial terrace uplifted up to 45 to 55 meters above present river beds. The corresponding return times of the great earthquake appears to have been order of 700 years since the middle Holocene, but we still have to work out on what was the influence, what was the effect of the climate change on those terraces. So we have differentiated between climate change effect and seismic effect. But what we believe is there is still some signal of climate change and seismic throws. So we are still working on it to separate these two. Thank you.
Covered a lot about the historical and prehistorical earthquakes in Nepal, including the latest technology, LIDAR, and the return period of the earthquake. Shall we go for questions or? Okay, maybe one short question. We are running out of time. If you have one question, okay, Professor Chai. I respect Professor Chai's suggestion. Okay, let's go for the next speaker. Thank you, Dr. Sapkota. Thank you.
Firstly, I really appreciate everybody that such a very much opportunity to come to Nepal once again, because 4 years ago, just after the 2015 Nepal earthquake, half a year later, I visited here with Dr. Suma and others. And that time, because Dr. Suma is managed the international workshop about Nepal earthquake, at that time, fortunately, because I'm living in Saga, and when I asked a lot of my friends in Saga to make the donation to the Nepal people, so fortunately, about 600,000 yen, finally we can get as a donation. Then after that, when I visited here, and with bringing the donation, After the international workshop finished, finally I to the person concerned of Nepal people under the witness of Professor Keiko Kitagawa at that time. So Dr. Smandi, thank you very much. So the keynote lecture schedule is already delayed, so I try to hurry to finish my presentation. So today's my presentation topic is the transition of soil structure in the high tide level change environment. So today's firstly, but shortly, I'd like to introduce myself. Who is Hino? So recently, the Japanese government is holding the research database. Or maybe this one's okay. Database called Research Map. So if you visit Research Map and just search Hino, then so there are the Japanese version and English version of the information for me. So if you visit the English version of my database, so you can search what's the guy. And also, I'm also managing the Facebook. In Facebook also, my ID is Takenori Hino. So if you are interested in my Facebook, please visit also my Facebook. So when I visit the other country and in front of the students, if I hold the lecture, then when I introduce the students that my handsome, because my photo is my cat. So if they are interested in my Facebook, so in the future, so please visit my Facebook. So please become friends. And then today's my outline of the topic is, everybody can see that this. Okay. So firstly, the landslide disaster associated with nuclear earthquake in Japan. But this one, just simply introduction, because I'm not familiar with disaster and landslide. I think after the presentation, maybe by Professor Hadarika and other experts from Japan, I think everybody can explain everybody well about the mechanism of the disaster, especially landslide. Then so next my topic is the measurement of the sensitivity of the soil. Then third one is the salt leaching phenomenon and the sedimentation of soil. Then last one is the development of the void in the soil. Then finally, I would like to make some of the concluding remarks. So first, my topic is landslide disasters associated with recent earthquake in Japan. So this is let's start to this one. So 2018 Hokkaido Eastern Evening earthquake. So when the Hokkaido earthquake hit Hokkaido, then that time also there are a lot of landslide disasters like this occurred. So when firstly I saw the situation of the damage of this earthquake, so soonly I imagined that this is like a landslide disaster in Norway by quickly. The situation is quite similar. And then this is a 2018 Indonesian Sulawesi earthquake. I just borrowed Dr. Sisak Swaroop's research achievement in YouTube. After the 2018 Indonesian Sulawesi earthquake, so soon Dr. Sisak Swaroop visited there and actually used the drone like this. Then so take the movie. So if you also visit Dr. Sisak Swaroop's YouTube, so you can clearly understand what kind of damage it is in this place. And after the Dr. Sisak Swaroop research finished, so Saga University members also actually visited this affected area. Very serious, very serious. So because we have a friend in Hasanuddin University whose name is Dr. Dori Harianto, and also in Paru. Paru is the central part of Sulawesi Island in Indonesia. I'm making a new friend in the University of Tadulako. So the doctor's name is Dr. Andy Lasden, who graduated Kyushu University several years ago. The two of my friends took us to the Dr. Sisak Swaroop's research area. Then when we visited there, so actually the damage is very serious. So especially, so this is one of the situations of University of Kathmandu campus. When Indonesian government developed the campus of the University of Kathmandu, so actually the Japanese Indonesian government also know in Peru there are a lot of earthquakes. So if people want to build the building, so up to third floor is a limit. So that's why when we visit the campus of the University of Kathmandu, so only the first floor building one, no problem. But the problem that in the campus, so there are a lot of the building at third floor. The most of the buildings damaged like this, especially at the first floor. So what I say? So damage and only now if we visit now, so this is look like a second floor. This is the third floor. But actually this is 1, 2, 3 floor this building has. So unfortunately, after the earthquake, especially at the first floor, several students working there. But after the earthquake, the building damaged, some of the students died. So very serious situation also existed in the campus of the University of Kathmandu at that time. And after that, we also visited some of the large-scale land disasters area. So the situation is like this. So I think the detailed information about this one. So primary, please visit Dr. Cesar Sorum's YouTube. And second, please visit my Facebook. So I think you can more detailedly know the situation of the earthquake damage. And after the large-scale landslide occurred, soon the Indonesian government tried to conduct the research using the boring machine. Actually, so this is an affected area. So if we observe the soil situation, because this is just after the earthquake, the state of the soil is almost reconstituted. So I think the next month, Professor Hadarika Himanta coming from Kyushu University to visit this part area and conduct their research. And that time, I think in the future, Professor Hadarika Himanta will re-evaluate the original condition of the state in the future. So maybe half a year later or 1 year later, that we can detailedly know the mechanism of this large-scale landslide by Professor Hadarika. Shall we expect like that? This is one of the main information using my lecture. After the earthquake finished, sorry, I don't mean a very fast, so I want to end here. Yes, okay. So after the landslide disasters associated with recent in Indonesia Sulawesi earthquake, then what we'll be talking about, because firstly is what Dr. Shintaro Mori mentioned about the Palu earthquake, especially the super large landslide disaster. He said like this: the 3 very large landslides in Palu, Sulawesi Island, Indonesia, may also be considered as a quick landslide mechanism. Then after that, what I asked him, so it will be very helpful. So I don't know how far it can be reproduced because it is after the earthquake. But I would like to do the boring survey. Then after that, what Dr. Shintaro Mori told me through Facebook, so what is the sensitivity of marine clay in Saga? Then what I answered through Facebook, in the past, there are cases that have shown 1,000. Can you believe the sensitivity ratio? The value is 1,000. But in my experience, 300 is the highest. Then moreover, I think that such high value is recognized in IT clay, like the intermediate soil, rather than clay dominant one. So for a while, so we exchange this kind of information through Facebook. Then, by the way, now what is the quick clay? So this is one of the very famous quick achievement by the Norwegian Geological Institute. So today, to this conference, Professor Masayoshi Kishodo also participating the 1991 Professor Shodo actually belongs Norwegian Geological Institute. So if you visit the Norwegian Geological Institute YouTube, then just to search this one, the quick play landslide at this side. Then so you can easily visit the NDI YouTube, and you can easily learn what is a quick play landslide through the YouTube video. And this is very famous data if we talk about sensitivity. This is a great characteristic of mangrove in Oslo, Norway by Bieland in 1954. So actually, I rewrote this figure using James K. Mitchell's textbook, which name is Fundamentals of Soil Behavior in 1993. So according to the Bieland data, so if we want to learn what is the sensitivity of the soil, then this is a very this is a typical data, especially why the sensitivity ratio become high. So mainly the remote shear strength drastically reduced because of soil leaching from the soil. So as a result, in the case of the Oslo, Norway, the sensitivity ratio is valued. For example, the upper part of this layer is the 75 of sensitivity ratio. And then middle part is 500, and the lower part also 500. So this means a very severe situation. If the sensitivity of the soil is very high, for example, so if we obtain the soil from the foundation with undisturbed state, so in that case, soil can stand up by itself like this, okay? But after the remodeling, like water. So if the sensitivity ratio is high, the state of the soil also drastically change like that. After this time, within 10 years, we already conducted more than 400 boring already. Then conduct the soil testing. Then so some of the soil testing, we also include to measure the sensitivity ratio of the grade. Then sometimes we also obtain this kind of data. So in the case of the sensitivity of acidic grade, actually from the viewpoint of the natural water content and consistency limit, the natural content always exceeds the liquidity limit. So it means that from the viewpoint of the liquidity index, we always obtain the value of liquidity index more than 1. Then on the other hand, so how about the sensitivity ratio? So usually, so under the project of constant law, so if we measure the sensitivity ratio of recently we obtained the value as around 20 to 40. But sometimes we also obtain the sensitivity value of 300, like this. Then, by the way, how acidic grade consists in the Sagaloran. This is the change in the sea level and the upper limit of flat bank deposited in the plain during past 10,000 years. From 10,000 years ago, so because the Sagaloran is just belong around the Adriatic Sea, the sea level of Adriatic Sea, that's 10,000 years ago, below minus 20 meters. But from 10,000 years ago to 7,000 years ago, so there is 3,000. So the sea level rapidly rise. So because of global warming. So this transpiration, so that time in Japan, the era is Jomon. So therefore, so finally this transpiration called Jomon transpiration. Then so especially from 10,000 years ago to 7,000 years ago, that's more than 20 meters sea level up. So as a result, and also, so for example, if you visit RHC, that's around Sagaloran, the typical phenomena of RHC, so we can introduce everybody like this. So the flow condition of RHC is counterclockwise flowing. And then especially the full moon or nothing moon, then tide level change become very high. So maximum is more than 6 meters. So as a result, so how this lowland developed like this as a result? So for example, so this the blue line is just 6,000 years ago. Then the black dot line is just 1,800 years ago. Then red line, red seashore line is 300 years ago. Then the final one is now. So after this blue line to this black dot line, so naturally the plain area expands. But so from black dot line to now seashore line by man-made degradation. So this is one of the developing history when we talk about Saga Plain. So under this condition, so in this plain, Arctic Ray, the average thickness of Arctic Ray is about 20 meters in this Saga Plain. Then we sometimes obtain the Arctic Ray and conduct the soil testing. So sometimes we can observe this kind of high density degradation. So this content, what I want to talk about, because I don't want to talk about describe the mechanism about mentioned disasters, especially the landslide mechanism something. So I probably depend on the more expert in the conference. So instead, what I want to talk about, the speaker will keep keen interest in the atmosphere where the perspective of the sensitivity of soil has become indispensable even in the field of landslide disaster. So next topic is measurement of the sensitivity of the soil. So this is the equation of the sensitivity of the soil. So if you open the electrical book, you can easily understand the equation of the sensitivity. So Chu is the unconfined compression strength of undisturbed soil. And so this Chu means is the remote strength of disturbed soil in unconfined compression strength. For example, in the case of Arctic Ray, so when we obtain the Arctic Ray in undisturbed condition, so it's a standard. But after disturbed, so this becomes like liquid. This is one of the typical characteristics of Arctic Ray. And so in the case of Arctic Ray, especially after this remoted, so the state will become quite liquid. Then in that case, usually according to the textbook, so if you measure the remoted strength of unconfined compression state, disturbed, and you can make the cylindrical equation once again and set it to the unconfined compression state apart, then the conduct unconfined compression state again. So this is the usual way. But in the case of Arctic Ray, so because of the liquid, it's easy to make a liquid condition. So instead of using unconfined compression test to measure the cylinder R, so we use this one, laboratory bench test. So how we conduct the laboratory bench test? So after unconfined compression test using undisturbed soil, the specimen and the shaping stored in the water content in various states added. And these are put into the plastic bag and milled until the field of aggregate is lost. And second, after measurement of the water content, it is packed in the cylindrical container. In our case, the size, diameter is 70 millimeter, and then the height is 70 millimeter. And we also use the band, but the foreplate, the diameter of this band is 10 millimeter, and the height is 20 millimeter or less. Then, however, when we pack the cylindrical container, so we follow the rule of Japanese Geological Society standard called JGS 0821-2009, and then packed over 3 layers by tapping about 30 times in 1 layer. And the third one, finally the surface of the cylindrical container is smooth, and after measurement of the wet density, they set in the this one. Then finally, so we can enter the BNC strength with the rocket to 90 degrees. Usually it needs 15 minutes at the rotational speed of 6 degrees by minute based on ASTM E4648, E4648, and 16 to obtain the result. Then after that, we obtain the remote shear strength of the soil using laboratory shear test. Then we obtain the sensitivity value. But so when we obtain the sensitivity value using the laboratory shear test, so we must a little bit notice about this here. So we sometimes put this parameter is QU, but QU means from the viewpoint of the molecular circle, the QU is here. But so for example, to measure the remote shear strength, so at that time, if we use the laboratory shear test, maybe so what we are measuring, maybe it's this dot. So therefore, so if we obtain the sensitivity using the laboratory shear test, in that case, maybe equation should improve a little like this. We sometimes mistake to calculate. So especially if I ask students to conduct to measure the sensitivity, to please bring the results. Then I think 1 week later, the student bring me the data, but the sensitivity rate is very big. Then what equation you are using? So students maybe answer me that because according to the statistical, the sensitivity introduced like this. But no, so because in that case, especially the remote shear strength, you are using laboratory data. In that case, you must improve the equation like this. So please be calculating like that. Why the so-called eating phenomenon occurs sensitivity become large? So because mainly, so because of especially the remote state become down. So because of so-called eating phenomenon from the soil. So as a result, so sensitivity increase. So this is the usual explanation if somebody talk about sensitivity. But the most important thing, I strongly believe that. So after the salt leaching phenomenon from the soil, so why undisturbed state, no changing? I think this viewpoint up to this time nobody explained. So in the case of articulate, so especially after the salt leaching phenomenon, I think shell portion melt, and then diatom remain also melt. So from the shell, so because of the melting, maybe so shell can supply the calcium material into it for water. On the other hand, the diatom remain can also supply the heat to the water. So if we observe the water quality of the water in articulate, now the water has a calcium, CK, and water. It means it is really like the treatment of putting quick-like or cell. So as a result, I think it's a natural condition. So because especially this phenomenon occurs after the leaching phenomenon. So maybe as a result, so maybe this kind of hardness it can occur. So as a result, so when we talk about the sensitivity, why after the leaching phenomenon, so especially this parameter no change, I think not only to decreasing the remote strength, but also develop the sedimentation in the soil. So as a result, sensitivity is coming. This is one of our factors. So if you down in the future, please obtain the grade, Kathmandu. Then please conduct, please check the sensitivity. Maybe the technical conclusion will be obtained. Then if you can obtain that, result I'll be very happy. But if I misunderstand it, so please teach me soon as possible. Okay? And then finally, my topic is this is one of the introduction of the unique state parameter to recognize by place cutting in Himalayan. So now in this case, from 0 meters to 50 meters, this is the data by horizon. And especially this part is a place cutting one. So according to the textbook, so if the depth increasing, the water content, so what I said, that simply decreases, right? But in the case of the Himalayan, So actually, in the porosity deposit, so lateral water content is increasing with increasing depth. So this is quite statistical knowledge. But on the other hand, so if we also obtain this deeper depth, so sometimes the water content is higher than the porosity deposit one, soft glacial one. So how we can explain to this condition? What do you think? So especially when to this soil, for example, when they start to deposit, maybe the water content is more than 1,000%. I don't think so. So that's why recently, so this kind of data we can obtain from Saganoran. So one of our also assumption is because in Saganoran, the geoenvironment drastically changes, especially all the sources go away. So as a result, so for example, if before the soil leaching phenomenon occur, maybe structure of the soil is really like this. But after the soil leaching phenomenon occur, maybe the soil structure becomes like this. So as a result, the sensitivity increase, complexity also increase. So that's why we obtain this kind of data. So here, what I want to talk about especially to be the development will also one of the possibilities. So please also check in the future. So especially why the development of the body in soil. So because if we observe the altiplane, so we also sometimes observe the biogenic pyrite. So the biogenic pyrite is equation to Fe and 2 of S, Fe-S2. So if this one will meet O2, so iron becomes like this, and so this sulfur so become like this. Then finally, especially this biogenic pyrite is melt. So at that time, if this void also becomes small, then no problem. But maybe, so after this phenomenon occur, the structure of soil is really like the piece in the Tom and Jerry's movie, like this. So this is one of the assumptions. So therefore, that's why now if we conduct the soil testing, not only by the Holocene deposit, but also the plain deposit, so we sometimes obtain this kind of data. So this is also now, so recent university groups assumption. So finally, so what is the concluding remark my keynote lecturer? Among the various soil data introduced in previous soil mechanics, so it is thought that there are many opinions that are being guided without well understanding of the sedimentary environment. And then second is reconstructing the initial depositional environment for comparison with the current environment, clarifying the mechanical processes that cause such differences, and then clarifying the effect of such mechanisms on the current environment, the unique approach adopted in the Saga-Roland area. Such an approach has been possible for the area because the area is blessed to have retained its original plane landscape since it was formed. We hope the data are collected based on a similar approach of the study nationally and then internationally, and we hope to have opportunity to discuss this at the same based on research. So finally, thank you very much.
Professor Suksam Harpi Bulsuk. Okay.
Will consist of 4 main parts, starting from the introduction, followed by the use of LS and MD blends for engineering field material. So LS stands for lateritic soil and MD for the Himalayan debit. And followed by the use of the blend with the cement to be sub-base and base material, and end up my talk with the conclusion. So I think most of the country around the world follow the ASTM standard, follow the onshore standard, including Thailand. So the backfill material normally is coarse grain soil or coarse grain material with very low fine content. So I would like to show you this picture to give you an idea about the coarse grain material available in Thailand. Our coarse grain material available is the lateritic soil because we are in the tropical country. And due to a lot of several construction projects in Thailand, the source of the material now become decreasing. So my talk today would be focused on the way of improvement of the the LS lateritic soil by using the replacement method and the cement stabilization method that are common in Thailand. And we have been conduct several research in Thailand in our university to prove or to confirm that the recycled materials can be used as the replacing material for the purpose of environment and the purpose of the economic point of view. We have been proved that recycled concrete aggregate, glass, the brick, and recycled asphalt pavement, those materials can be used as a replacing material. Today, I would like to show you one of the waste material that obtained from the manufacturing process of the PET, plastic PET, the cup, the table, the plastic table, that is the melamine device or MD. We have more than 400 tons of MD every year produced. So my talk today will show you how we improve the lateritic soil by using the MD as the engineering field material and also as the sub-base and base material. So first of all, I will start with the brain as engineering field material. So I showed you this one. You can see this one. This is the property of the lateritic soil that I choose for this study. You can see I showed you the red numbers because you can see that when I compare with the Department of Highway standard, the material can be said as the marginal lateritic soil because you can see the CBR is very low and the soil is very high. So we cannot use this material even for the field material. So I introduced the MD that you can see the property of the MD that the swelling is almost zero. Liquid limit is also almost zero. For sure that if you introduce the non-plastic material into the material with high fine content, you can reduce or you can minimize the fine content. And the fine content is not preferable for the geotechnical material. So you can see that I introduced the 20%, 20% to 40%, the material, the bench can meet the requirement as the engineering field material. And even I add more, up to 50%, the properties are close to that of the sub-base, but it is not the purpose today. The purpose is for the engineering field material. So you can look at the CBR improvement. This is a CBR improvement. I'm sorry, I'm not so familiar with this one. The CBR improvement. If you look at a particular compaction energy, you can see that the MD can improve the CBR value, but up to 20%. If it's beyond that, the improvement is not much. So the way to do it is you can enhance the compaction energy. So when you enhance the compaction energy, the CBR increases. But in Thailand, the CBR required for sub-base is 25. I think different country different. Let's say in Australia, they need 80%, but in Thailand only 25%. And you can see that if it is not the proper way, it's very costly. If I compact, if I increase the compaction, it means I need more and more money. So one of the best way is we stabilize by cement. That is the next topic I'm going to talk. And for the swell, you can see that we can reduce the swell significantly, and only 20% that I already mentioned. So the best ratio, it should be about 20%. So I show you what is the reason behind the improvement. How come we add the MD and the strength or the property can be improved? Because you can see that for the compacted material, the engineering property will be controlled by the property after compaction, not before the compaction. So it means that if we can minimize the breakage of the particle, the engineering property will be better, right? So I show you this one. You can see this one. This is the material, that's the MD, the gradation before and after the compaction. You can see more or less the same. But if you look at the property of the lateritic soil, that when you compact it, you break down the large particle and you get more silt content. You can see this is the silt content. You get more silt content and fine content. So if we have more fine particle, for sure engineering property will be worse. And if you look at this one, I show you this one. This one, that you can see that when we add MD into the material, the breakdown of the particle is smaller. So that's why this is the reason why we can improve the engineering property of the LS by introducing the MD. Okay? So the next topic I'm going to show you is we try to improve the material for base and subbed by introducing the cement. And four parameters I'm going to show you that they are improved. One is the strength. The second one is the CPR. The third one is the durability. And the fourth one is the leachate characteristic. That four main parameters are required for the sustainable road design. And the first one is the strength. According to our standard, the Department of Highway standard, we have for base and subbase, we require the strength of, we require the compaction energy of the modified at the modified energy. So what we have done is we compact the range with cement to determine the optimum water content. And at the optimum water content, we prepare the sample and queue for 7 days, 14 days, and 20 days. Then we soak it under the water for 2 hours. This is our standard because we want to simulate the fracturing condition. And then we dry the sample and perform the unconfined compression test. And I showed you this one. You can see that if I just use only the lateritic soil mixed with cement, the material would not be allowed based on the Department of Highway standard. Because this is the standard that I show you in the picture, that you can see that the liquid limit is over 40. It is not allowed. So how to do? We have to reduce the liquid limit before mixing with the cement. So what we have done is, you can see that if I add 20% or 40% of MD, I can reduce the liquid limit and it can be used for the stabilized material. And you look at this one, very interesting that if this one for 5% and this one for 3% cement. And for 5% cement with 20% MD and 40% MD, the material can be used for subbase material. In Thailand, we use only 7 days strength as the indicator, 14 days and 28 days just to look at the strength development. Okay, but for the 3% cement, the MD of 20% and 40% can be used as a subgrade material. One of the interesting points in this one is, you can see that if I add MD, the strength decreases. But anyway, even if it decreases, it still meets the requirement. It decreases because the MD itself has high water absorption compared to the soil. So when I mix the MD with the soil, what happened? The optimum water content increases. And I already mentioned to you that in Thailand, we need the strength of optimum water content. So that's why when we add the same cement content, but with high water content, for sure the water to cement ratio decreases, the strength decreases, right? So I will show you how the MD improved the CBR. It improved CBR significantly, different from the compression test. Because in the compression test, we only soak the sample for 2 hours. But for CBR, I think everybody knows that we soak for 4 days. When we soak for 4 days, what happened to the sample? Because the soil is laterite soil, the permeability is very low. So it takes really long time to absorb the water. So you see the trend of the strength development decreases with MD. But if you look at this one, the CBR, surprisingly that the CBR increases with MD. Because in case of the UCS, the unconfined compression test, you just test at 2 hours of soaking. The sample is not fully absorbed the water. But in case of the CBR, it absorbs the water more and more and fully absorbed. So what happened to the cement stabilized material? If you have very high swelling, or even we can say swelling pressure, or swelling, they are related. If you have more swelling, what happened? You break down the cementation bond. When you break down the cementation bond, the strength decreases. But if you look at this one, you look at the swelling result, very interesting. Without the MD, the swelling is very high. But once we introduce the MD, the swelling decreased half. It means that you minimize the swelling pressure. Then you can see that the CBR increases. This is the advantage of the MD improvement. Okay, this is the advantage of the MD replacement. But if you add more, it's a bit decreased because the initial strength is low because of high water to cement ratio, as I mentioned. The next one is, I show you the durability test that the MD can work very well. It improved the durability. Since in Thailand, I think everybody knows that we are in the tropical country. We have two main seasons. Somebody may say, no, 3 seasons. We always say hot, hotter, and hottest. But just joking. Okay, but we have 2 main seasons. One is the rainy season. Another one is the dry season. Somebody call wet season and dry season. Okay, so the most appropriate durability test is the durability test against wetting and drying. So we perform the test according to the ASTM standard. And this is the summary of the test based on the ASTM D559. So what to do is, after we get the sample at optimum water content, we soak the sample for 5 hours under the room temperature. And then we just chill the sample for 42 hours at 70 degrees Celsius. This is just to simulate the wet condition and it is for the dry condition. So that's why we can call this cycle as one wetting and drying cycle. So what we have done is we prepare the sample for 12 number of cycles. Then we perform the unconfined compression test at each cycle. And I showed you this is the interesting result. In this figure, I show you the result of the only for the bench material. Only for the bench materials, not for the soil satellite, not for the soil. Because after second cycle, the stabilized soil was damaged, no more strength. So from this one, this is you can see we have 2 sets of the sample. One is the open symbols, the other one are the black symbols. The open symbols are for 5% cement, and the black symbol, the dark symbol, are for 3%. Okay, and this one for 20% and 40%. And if you look at this one, you can see the same trend, that the strength increases. The maximum value is found at 3 cycles. Based on our experience, we have found this result. And you know, first when I saw this one, I mean, everybody's surprised. How come when you perform the wetting and drying, you use, when you dry the sample chink, but once you wet the sample swell. Swelling and shrinkage must damage the sample. How come the strength increase? But we have conducted several tests, not just already material, other materials, and we found the same. So we published this concept in several papers. And what we think is because the crack developed at the initial cycles is benefit to strength development. Why? Because the crack developed at the initial stage is micro. So when you have the micro crack, the water can penetrate to the sample. When the water penetrates to the sample, it reacts with the cement grain. We can say unreacted cement grain. Because when you add the cement into the material, it is not 100% reactive with water. Some are not. Then when you have the micro crack, the water can penetrate to the sample and react with the cement, the strength increases. But if we have more and more number of cycles, what happens? It's not just only the micro crack, but the macro crack develops. With the macro crack, the sample is damaged and the strength increases. Okay? So I showed you this one. This is the proof that the macro crack damaged the sample. You can see it after the second cycle of the cement without MD, the sample failed because it swelled a lot. But MD can minimize the swelling. And if you look at this one, you can see that 3% cement, the weight loss is very high, up to 70%, very high. That I already mentioned to you that it is not micro crack, but it's macro crack and damage the sample. And I summarized my result with comparing strength, weight loss, and the surface environment. You can see this one. If you look at the maximum values here at third number of cycle, you can see that maybe you cannot see properly, but the sample is still, I mean the surface is still look good. Okay, with the small cracks, we can call it micro cracks. But with higher number of cycles, you can see for 3%, the upper one for 3% and below one are 45% cement. But for the upper ones, you can see the sample trend almost failed. There are a lot of surface crack. Okay. Then the last topic I'm going to present to you is the leachate test. That we have to make sure that because we introduce the waste material, we introduce the waste material into the good material or into the natural material. For sure, if you have laterite soil, it's a natural material. Nobody concerned because it's natural. But when we add the MD, it's waste material. When people talk about the waste, people are afraid of the waste, right? So we have to make sure that we would not harm the nature. We would not cause any problem to the water resources. So what we have done is we perform the test, so-called the TCLP. CTLP stands for the toxicity characteristic leaching procedure. Okay? And 3 types of materials we have been prepared. One is the MD itself, just to make sure that what is the leachate, what is the heavy metal in the MD would be leachate. And how can you say, hey, this material is safe? this nobody can say this is safe, because when you get the heavy metal leachate, how do you say, hey, this concentration is high, this concentration is low? Is it harm to our body? How we know? Simply drinking water. Because the drinking water, we drink water every day, but we're still okay. So we have to compare the concentration with the drinking water. So this is I showed you this is the concentration by the EPA, the concentration of the EPA, the accepted concentration in the water that you drink and you save. So we compare with this one. So what EPC suggests? Because when you get the water in the water resources, it is not directly to our body. We have to treat it before drinking, right? So EPA said that, okay, the accepted concentration is not over 100 concentration in the drinking water. So I show you this one, it's very safe. I show you the result that this is the result for the soil stabilization, and this is without MD, and this is with MD. You can see that all the concentration of the heavy metals concentration are lower than 100%, 100 times of the concentration in the water. So we can use the MD as the sustainable waste material. So I would like to end up my talk with very simple conclusions that the MD improve the engineering property of the marginal lateritic soil and can be used as engineering fill material because the LS minimize the weightage of the large particle. And we can confirm that the MD is the environmental friendly construction material. Thank you very much. And if anybody interested in my talk, you can go through the 2 papers that we published in Journal of Cleaner Production and Road Materials and Design. And one more paper is coming out on the leachate properties that will be in the environmental geotechniques, maybe very soon. Thank you so much.
Thank you, Professor Sakshun, for a very interesting presentation on potential application of melamine debris, covering the physical properties, mechanical properties, and the environmental impact assessment. Thank you very much. Let's give you a big hand. Okay, our last speaker is going to be Professor Suichi Hasegawa. He is presently a professor at the Faculty of Engineering and Design in Kagawa University, also Dean of the same faculty. He was also president of the Japan Society of Engineering Geology, and he is currently a research member of Japan Geopark Committee. He got his undergraduate, master's, and PhD degree from University of Tokyo, and his research interest includes engineering geology, geological hazards, and geopark promotion. Professor Hasegawa, please.
Himalaya is situated over the collision zones of Indian Plate and Eurasian Plate. The broad convergence between those 2 plates has resulted in mega earthquake around the Himalaya. It's a common knowledge, and surprising during Golka earthquake, the higher Himalaya here has. I'm confusing. Oh, okay. I aim of this presentation here. Next. First, I'd like to Asia, and I'm surprised because during Dorka earthquake, higher Himalaya subsided. On the contrary, the Kathmandu Valley was raised by 1 meter. This is, how do you explain this phenomenon? What is the cause of uplift of higher Himalaya? I noticed that Miocene leucogranite is only distributed in higher Himalaya. Miocene's younger age is about 20 million years ago. This is a picture from mountain flight. This is Everest. This white, sorry, it is very difficult to. This white rock is Miocene leucogranite. Miocene leucogranite of low density might be the cause of uplift of higher Himalaya due to buoyancy. After the intrusion of Miocene granite, the Himalaya had reached sufficient elevation by around 10 million years ago to produce the Indian summer monsoon. As a result, flooding and landslide are frequent in monsoon season during summer. This figure illustrates the topography and 24 hours maximum rainfall in Nepal. Dr. Ranjan Kumar have unveiled here and recognized this large-scale landslide occurred within the more large-scale landslide masses. Let me show some examples along the large-scale landslide along the main road in Nepal. This figure shows large-scale landslide topography distributed along Muguri-Nagarayat road. Along the highway, this many rainfall-induced landslide occur. Let me show some example. This shallow landslide is occurred in the occurred at the margin of a large-scale landslide. You can notice this is shallow landslide, but this area is a large-scale landslide. This next slide illustrates the relation between shallow landslide and large-scale landslide. Large-scale landslide is deep city landslide, but it is only shallow landslide occur during rainfall. I have a question. What caused this large-scale landslide? This figure illustrates the relationship between shallow landslide, small-scale landslide, and large-scale landslide. And present Nepal road is along the contract. So it is very, it is very environment friendly. It only cuts the surface of large-scale landslide. But Nepal is now developing, so the fast track road is climbing. So fast track road is straight, they cut the required high cut slope and long tunnel in large scale landslide material. So future express highway in Nepal will require the high cut slope in large scale landslide material. This is a present road cutting, very shallow. So the material made, most of cutting material is soil, but in future, high cut slope cut of bedrock or large scale landslide mass. It must be the slope study problem. Let me show some sliding surface of large scale landslide. This is a sliding surface mainly composed of clay materials. Main clay minerals are mainly chlorite and calcite. What was the cause of large scale landslide? This sliding surface of clay mineral of the key of this question. This map shows the distribution of eugogranite. Eugogranite is distributed in higher Himalaya, and hot spring. It is called Kathmandu in Nepal, distributed mainly in higher Himalaya along the main central thrust. This indicates hot spring. It means hydrothermal high solution. Let me show some example of Kathmandu on the foot of Annapurna Range in Nepal Himalaya. Here is a hot spring. The local people enjoy hot spring, but I haven't. This figure illustrates the relationship between hydrothermal alteration related Miocene volcanism and that affect the surface geology of surface geology. Hydrothermal alteration due to the granulation of Miocene granite is the geological cause of deep sea landslide, because this hydrothermal alteration form the clay minerals such as calcite and chlorite. This shows another sliding surface of large-scale landslide. You can notice this brecciated clay and brecciated layer, and just above the clay and brecciated layer, there was some just little fractured, but not sheared bedrock. This means this clay and brecciated zone was formed by not faulting, but hydrothermal alteration, because the fabric of this breccia is random fabric, not shear fabric. In Nepal, there are many kinds of such fault as a shear zone. Present road is cut is very small, so the cutting materials may be soil. But future road cut the bedrock, so it might be meet this shear. That's a future risk of fast track project. And also tunnel excavation. This hydrothermal alteration is very trouble. Let me show some example in Japan. In Japanese highway in Shikoku, there are highways located along the active fault median tectonic line. Along the median tectonic line, there are many landslides and suffered hydrothermal alteration. So we characterize the whole mass of tunnel mass by the affection of hydrothermal alteration and landslide. So let me show the conversion of this type, four-type tunnel graph. So it is very important to recognize hydrothermal alteration along the fault, but it is very difficult because surface material is weathered, so it is very hard to distinguish weathering or hydrothermal alteration. So boring is very useful to identify the hydrothermal alteration. Moreover, we notice a large-scale landslide. But if the landslide is old and dissected, the landslide topography is dissected after its formation. Let me show some dissected large-scale landslide. Tansen is located on large-scale landslide mass. This is second stage landslide. The body is located to the east. And let me show some topography and rock mass of landslide material. This rock is landslide scarp, eroded, and many channel is produced. This is a landslide mass. Let's look at closely. This is very fractured and fragile. And most of fragile rock at the Himalaya was not caused by tectonic activity, but surface deformation by ancient landslide. That's my idea. This figure shows the degree of dissection and formative age in Japanese large-scale landslide. Topography of large-scale landslide have been completely dissected after 1 million years. But landslide body material have still remained. Kathmandu Valley, I'm interested in Kathmandu Valley. The Kathmandu Valley is very abnormal. Usually valley located like this, low area. But Kathmandu Valley is very high. So high in elevation. How Kathmandu Valley has been formed? I am interested in the two parts. At present, Bagmati River outlet of Kathmandu Valley is southern part, Bagmati River. But there is two hills near Saku, Nagarkot, and this western part. this might be large-scale landslide. This is my guess. And Changnaraya Hill and Suanabu Hill also the landslide mass. This is the outlet of Kathmandu Valley. There is a large-scale landslide like this. So, but this is too small to form Kathmandu Valley. Sometimes it dammed up and produce lake, home lake, and burst out. But it is not the origin of Kathmandu Valley. One possibility is here north of Nagarkot. This is a branch of Indravati River. Indravati River must flow from here, and this large-scale landslide dammed up and northern at the eastern part. And this is a Changnaraya Hill. You can notice this is a long ridge, but it is separate from this ridge. This map is very useful to identify the ridge break. Ridge break indicates the large-scale mass movement. This shows rock mass condition of Changnaraya Hills. It is highly weathered like soil, like sand, not sandstone, like sand, but by structure very fractured. Why so strongly weathered? Because highly fractured rock mass is easily to weather. Let's show another example, another possibility of large-scale landslide in the west part of the Kathmandu Valley. This must be slid from here, and the second stage landslide occurred after the first slide. This is the main cause of Kathmandu Valley. Kathmandu Valley was a composite landslide dam. And Suanabu Hill is located on the margin of large-scale landslide mass. Yeah, this is a picture of large-scale dissected landslide. It looks like just a hill. But my hypothesis is true or not is proved by next tunnel project construction might be prove my hypothesis. Why this large-scale, huge landslide cut? One possibility is subductions of an earthquake. But in 2015, we don't observe such a large-scale landslide. Previous topographical, geomorphological, and geological research revealed that there was a MCT like this, and another active fault run like run like this. So it is difficult to identify the active fault beneath large-scale landslide, but there is one possibility. Yeah, this hypothesis is related to the damage of Gorkha earthquake. Surprising fact is, evidence is, Gorkha is very safe. They have suffered little damage during the Gorkha earthquake. Because Gorkha is located large, huge landslide mass. This picture shows the damage of the Kathmandu Valley. Tall tower and building, damage of tall tower and building is severe, but fragile, short stories houses were safe. Interesting fact is, Midland located is Kathmandu is located in Midland. Midland is uplifted during earthquake, Gorkha earthquake. So landslide must be occurred mainly in Midland, but the earthquake-induced landslide mainly occurred in higher Himalaya and southern Mahabharata range. How do you explain this? This is a picture of Midland and higher Himalaya. We visited two higher Himalaya area and Midland area, and we first checked the topographic effect. F value means uses slope and curvature. It means topographic effect during earthquake. So I don't know the maximum ground acceleration during Gorkha earthquake. So we assumed 200 gram, 300 gram, and 400 gram. This map shows landslide occurrence in higher Himalaya. If F value occurrence is according to F value, but Midland is almost very few landslide occurred. F value means only topography. So this means that bedrock conditions quite changed, different between higher Himalaya and Midland. In PGA, 400 gram is same relation. So the bedrock is quite different in Midland. This picture shows higher Himalaya. Slope is very steep and rock is very fresh. This is Midland. Slope is very gentle and bedrock. I don't think bedrock, but I have to say for bedrock is very fragile, flaky, fractured, and weathered. So my hypothesis is fractured bedrock in Midland might be act as cushion during Gorkha earthquakes. So the tremor of short period was attenuated, and long tremor of long period remained. This might this shows Kathmandu damage of Kathmandu here. Fragile houses remain, but high tall tower, only tall tower collapsed. So I think the Kathmandu Valley is very lucky. So it has two cushions, basement cushion of landslide mass and surface cushion of thick lake deposits, like stream deposit. This is my idea. So it is, I'd like to propose, let's promote UNESCO Global Geopark in Nepal, because Himalaya is most significant geologically and geophysically most significant area on the earth, but there is no geopark in Nepal. UNESCO Global Geopark is a single unified geophysical area where sites and landscape of international significance are managed with his holistic concept of protection, education, and sustainable development. Now, UNESCO Global Geopark is an official program of UNESCO. So, this is a sustainable education, conservation, sustainable development is the aim of Geopark. And Geopark is not only topography, geology, but ecosystem and human culture and history, or everything related on the earth. So, let's promote Geopark in Nepal. Thank you for kind attention. Without help of Dr. I cannot do this presentation. Thank you.
Thank you, Professor Hasegawa.
First, we will start for the introductory presentation from the Congress sponsors. So we have two presentations. One is from McAfee and is followed by introduction to Trommer Geotech Solution International. So we have strictly for the McAfee we have only 15 minutes for the presentation, and then for Geotech Solutions of Trommer only 5 minutes.
I'm Vasudeva Pokhrel from McAfee. Not discussing, but talking about McAfee, which has an experience of more than 140 years. In McAfee, we have an experience of 140 years. And in these 140 years, we have researched, designed, and developed solutions to solve technical problems within the civil engineering, geotechnical, and environmental construction markets. To become a leading international provider for advanced solutions to the civil, geotechnical, and environmental construction markets. For this, we research, we manufacture, design, supply, and we construct. Our vision is we strive to be a technical reference, solving our clients' problems through innovative collaboration and best value environmental solutions. We value high the integrity, respect, excellence, innovation, global experience, and local knowledge. And these values, our values, are the foundations of McAfee, which have defined our mission and our successes for 140 years. In terms of integrity, we are transparent in our behavior. We keep our promises, assuming full responsibility for our actions. We respect the contribution to the quality of life by leaving a better environment and community for those who follow. Our excellence is by improving our performance and services to become invaluable to our clients. In terms of innovation, we are investing to affirm our reputation as pioneer in all our businesses, and global exposure and local knowledge in all 5 continents, more than 100 countries, enable us to be simultaneously global as well as local. Our motto is engineering a better shore. We believe in balanced and sustainable growth. For this, we pursue diversification both geographically and with the business sectors in which we are. We believe this reduces our exposure to risk and promise our opportunities for growth. Thus, we design our organization to deliver our global experience and technical capability at a local level. McAfee, we were established in Nepal in 1995, and I'm very much thankful to Professor Suichi Hasagawa, who, while describing the protection of, infrastructure development works near Kathmandu, in fact, in this area, from Thanpur to Novis area, at several locations, we had done our protection works in our early days, somewhere in 97, 98, which are excellent, and today also whenever we are moving along those roads, as well as through Mughalinar and that roads, on either side, uphill and downhill of the road, we can visualize those structures very properly. And in McAfee, we don't believe selling our products, but we believe to provide a better solution and by identifying, addressing, and responding to the specific need of each client, so that we can deliver the best solution. This is where we are existing in Indian subcontinent, and our market sectors is starting from transportation infrastructure to mining, coastal and river control works, emergency and floods, the environmental protections, the military, oil, gas and energy, urban infrastructure, building industry and sports, and agribusiness. The key applications are soil enforcement, retaining walls and soil reinforced structures, erosion control, rock protection and snow barriers, soil establishments and pavements, coastal protections and pipeline protections, hydraulic works, drainage and structures, environmental dewatering and landfills, tunneling, safety and noise barriers and fencing. These are the application areas. In this slide we are trying to explain where in practice we are working. Like you can see coastal protections, marine structures and pipeline protections, or aqua structures and waterfront. Then rockfall slope barriers and hill slope, environmental dewatering and landfills, the road and pavements, in tunnels, in dredging structures and soil reinforcement structures, roads and hydraulic works, drainage structures, erosion control, basalt enforcement. These are the areas that we are usually working, and we have tried to show in photographs as well. These are some of the principal markets we are involved in: is infrastructure development, mining, environmental protections, coastal and river control works, and urban infrastructures. And here, I will try to describe mainly with reference to road, where we can have our collaborations. Say in hillside, rougher area, the slope protection netting, the soil laying, rougher embankment, simply to prevent falling debris towards the road or damaging roads. Then on roads, the road pavement reinforcement materials, and downhill again the conventional to reinforce soil structures and drainage management. Some earth retaining structures with reinforced soil using reinforced soil concept. It is in Geologist, very near to Kathmandu. In Gokarna, again very near to Kathmandu. It's in India. You can see both the gaseous phase as well as green phase. Again, in Sikkim in India, a fuse. Just to inform you, in this particular project, we have designed and constructed a wall, reinforced ballistic wall, with 80 meters in height. Some more reinforced ballistic on the side of course. We can see the roads on the other side as well. Some more examples of reinforced ballistic reinforced ballistic with concrete phase. In this instance is in Kathmandu, and Kathmandu mining project, again supported by JICA. In India, reinforced ballistic structure. The gathering structure in India is Mumbai-Pune Expressway. Now coming back to Rappal barriers, example of Rappal barrier. During construction of Rappal barrier, taking up the material to hilltop is being taken up with the help of helicopters. Again in India. Now coming back to pavement, is roadways being laid, is glass grid. Coming further now to environmental protections, we can see storm drainage, we can see pond lining, again pond lining, canal lining. This again moving Narayan Road sector, we can see the object protections. Whenever we have opportunity to pass by this road, we can closely visualize these structures. What we can see from the top is concrete topping, but in total it's gathering structures covered with on the surface with concrete. Again moving Narayan. Some more riverfront structures in India. Riverfront structures in India is geotubes and geogads for bank protection. This is use of geosynthetics in river Brahmaputra in India. In river protection in Orissa in India, and this is one more excellent structure showing use of guidance with defined arcs. So with this, I think I did not delay the defined time value. I conclude my presentation there.
So today I will be briefly introducing what Trumor Bautan and Geologic Solution has been doing in Nepal. So Trumor is an Austria-based company. It was founded in 1991, and they have been providing services in the field of protection of natural hazards, especially in the field of rockfall catchment fences, debris flow barriers, avalanche protection, rockfall slope stabilization products, and gradients. In case of Geologic Solutions, we were established in 2015, and we are located at Nepal, Lalitpur. So we also provide engineering consulting services in the field of disaster risk reduction, and we are the pioneer to bring the Austrian technology in Nepal Himalayan. So till now we have successfully, these are the services we provide, and basically till now with the Trumor we started our collaboration since 2014, and then in 2015 we jointly installed a pilot project in Siddhababa Highway, especially for the rock barriers and slope stabilization with high performance netting. And in 2016, commercially we installed a rockfall protection system in Upper Hotekoshi hydropower project, which has been damaged by the 2015 earthquake. So these are some examples of Siddhababa rockfall protection system that we have done in all these whatever resources we have, and we completed the rockfall barrier as well as slope meshing also. And the system has been working quite well. Similarly, we did the same rockfall barrier system in the upper Kotekoshi hydropower project also. These are some photos of the hydropower of the work. We work in this terrain. You can imagine how difficult it was. It was the first time we installed this kind of system. We don't have any already installed system, but we customize whatever resources we have and install it very successfully. These are some examples how we work in this kind of difficult terrain. And this is how, with the help of Nepal's Army helicopter pilots, we will successfully install these posts where the access is very difficult. And the system is also like they have been performing quite well. The main advantage of the system is you can just remove the debris that has been cast by the system and you can reuse it again. So we can see these big boulders have been cast by the system and the downstream was quite safe. These are some examples of the boulders that have been stopped by the barriers. So we are also planning to introduce this kind of soil naming system in Nepal. These kind of systems. And what we want to show, inform you that all of these trauma systems are certified by full-scale tests. And we also have all the certification specially given by the ETAG 27. These are the certificates of all the products. And how we do this kind of work is, whenever our client requests us to provide a solution, first of all we do the field survey, and then based on the field survey we do the simulation, and then based on the simulation we will provide the barriers as well as slope meshing system. So these are some examples of rock simulation that we do in case of Kotekoshi. And trauma Sultan is already established in Europe, North America and South America, and we established them in Nepal as well. And right now we are working on the product authorization for tumor also. In our team, beside the tumor technical team in Nepal, we have this is myself and this is another engineer, Sunil Paul, and then you all know Dr. Dahar, who is the president of NSEG. He is in our team, and Professor Hasekara is our technical advisor, international advisor also who is supporting constantly in our projects. So I will not be taking a long time. So we are ready for any kind of geotechnical solution. If your projects need any kind of solution, please contact us. This is our contact address. Thank you so much.
Time to honor our keynote speaker, founder president of NSEG and convener Dr. Ranjan Kumar Dahar, to present a token of law, and then I'm going to announce the name professors. So first of all, I would like to call world's top geosynthetic and ground improvement Professor Dennis Bargado, to receive the token of law. Next keynote speaker, Professor Dr. Takenori Hino. Please. Similarly, I would like to call Professor Dr. Suksan Hartibilsuk. So is he here? I just get to know that he was so I would like to call Professor Dr. Suizi Hasegawa to receive this honor. Honor with the token of law for session chair. So I'd like to call Professor Dr. Hemant Hazarika on the stage. Please receive your token of law. Subscribe here in the room. So please receive our token of law. Professor Dr. Hemant Hazarika to receive the honor. Now is doing my stuff.
This proposed test is applied to collapse site of natural slopes in Japan. One is disaster heavily rain in the northern part of Japan, Kyushu, Japan. And another site is same Kyushu Island, but a different period. So before explaining the simple result, first I would like to explain in-situ direct shear test. We developed this kind of portable direct shear for in-situ strengths. But sometimes it takes time to perform this test for getting strength parameter because we need to plot and obtain C and Y. And I apply this direct shear test on the solid waste material ground. But we need to cut for making specimen. Sometimes we use electric cutter, but 1 or 2 days, it takes time for 1 or 2 days for obtaining strength parameter of this solid waste material. So this is the reason why I propose another simple in-situ test. And this is the portable cone penetration test. And this is the pull-out test using the spiral pipe like this. And in this concept, cone penetration test is for obtaining bearing capacity, and the pull-out test is for obtaining frictional resistance. But if the ground has a frictional angle, frictional resistance increases in depth like this. But when we apply this pull-out test in different depths, we can get this cohesion. This is the concept of this idea. After we perform, we did this test on the solid waste material ground. Because we perform this test quickly, and we can estimate the strength in different position. And for making clear the validity of this test, this graph shows comparison of cohesion by direct shear test and spiral pipe tunnel test. There are some relationship between cohesion of tunnel test and direct shear test. And
It's called the storm wave. This was the situation, this was the hypothetical model that I produced. In this case, you can see that the opening is there, and when the lateral force is here on the top, this wall, which is opposing the resistance, will contribute to certain length, like Kx, which will contribute in resisting, and the top portion will not be compressed because it is open. If it had been fixed up to here, if the wall extends up to here, there will be a contribution of the compression from the beam as well. But it will not happen in this kind of case. So here you will see that this Kx was what we obtained first, and then with some geometrical calculation, try to find out what would be the width. I did the work for all these cases, and then the stiffness, period of vibration of the building, and the shear forces
were studied. Similarly, those studies were done with the bare frame as well as for fully infilled frame also, as I told you earlier. Then the partially infilled frame was done study for 90% to 10% to 90%. That means firstly we put 10% wall and then 20% and then 30%, as like that it reached to 90%. So always there is a problem like what would be the compressive strength of whole masonry. It is very simple to find out what is the compressive strength of brick, because you can do the compression test and you can get the compressive strength value by taking the results from the compression testing machine. But when it comes to the wall, then it becomes a problem. So for me, it was difficult to get this FM bar. So what I did was I tried to look at the FEMA 273, in which you will get these three values with the range. If the wall is very good, then you will put it as 6.3 MPa. Otherwise, fairly conditioned one will be 4.13, and the poor condition 2.07. For my research purpose, I used the value as 5.6, which was somewhere in between these two. And then this is an expression to get the Young's modulus of the masonry wall. Because as I told you, to get the Young's modulus of a brick is also easy, because it's already available in the documentations. But to get the the data for the Young's modulus of the masonry wall, then it is quite complicated. So I had to look for some work done by NSJC 2011. This is the expression. You just simply put this 5.6 over here to get the Young's modulus, and you enter that value in the computer program.
Ladies and gentlemen, thank you for the invitation. It's my first time in Nepal and here in Kathmandu. Nepal, very impressive case studies. I would like to show you some case studies from the Austrian Alps, and my presentation is called Process Analysis, Investigation, Monitoring, and make a modeling of deep-seated rock slides. So these landslides are already fractured rock masses in metamorphic rock masses. In introduction and classification, investigation and characterization of these deep-seated rock slides, monitoring, different types of monitoring for these different rock slide masses, and finally a short part about numerical modeling. I will show three case studies from the Austrian Alps, and then I will finally make a short conclusion. Oh, wrong way. So, short introduction and classification. So all these case studies which I would like to present are case studies from the Western Austrian Alps. The mountains are about 3,500 there, and some of these case studies are very well investigated because they are in the surroundings or they are located to big dam reservoirs. So there's some hazard. So we need boreholes, there are investigation drifts, and a lot of other investigation and monitoring methods. All these rock slides are metamorphic, foliated rock masses, so barren gneisses, mica-schists, so metamorphic rocks. And before I start, I will give short words on classification, the terms I would like to use. So this is based primarily on the EHG from Kroon and Vance from Vance 1996. A slide is a downslope movement of a soil or rock mass occurring dominantly on surfaces of rupture or on relative thin zones of intensive shear strain. So we have a shear zone with also internal shear zones. Ulrich Hanger and his group et al. 2014 published a new update of this classification system. And these rock slides I would like to talk about are rock compound slides. They are characterized by sliding of a mass of rock on a rupture surface consisting of several planes or a surface of uneven curvature, so that motion is kinematically visible only if accompanied by a significant internal distortion of the moving mass. So we have shear zones, we have basal shear zones, we have internal shear zones, and we have a strong fracturing of the rock mass, so the porosity increases and the hydrogeological system of these rock slides changes.
Example of where you have a system all connected to one digitizer. So you can have a subsurface instrument, a strong motion instrument, a weak motion instrument if you wanted to actually monitor general earthquake activity, and then all connected to a GPS for timing. So this is the final slide. So this is a surface instrument which is currently being developed. Now we have seen quite a lot of demand for instruments to go on the surface for general noise surveys and for rapid deployment in aftershocks. Now this can fit easily into a backpack. It means that you can very, very easily get to your sites quickly after a major earthquake, and you can then put this on the ground. Then this uses the same technology as the radian, where it doesn't matter if it's upside down or on its side, it will readjust all of its components so that if there is some loose soil, then it doesn't affect any of your data. Now that was the end of the presentation, so if there's any questions, I'll take them back.
Did very well. We have time for one or two quick questions.
Very much for your nice presentation. So in your slide, I have seen one that you are going to build something like the 600-meter borehole. So you're just sending the sensors using your Google or somewhere? Please.
So is your question whether Bharat is planning to do it or if there are plans to do it?
Yeah.
So there are currently no plans within the Kathmandu Valley, although there are multiple. I'll stand over there. There are multiple plans in the UK for such systems, currently being carried out by the British Geological Survey. They're monitoring lots of sediments in the north of the UK, and it's just completely applicable in Kathmandu as in the UK as well.
Okay. Thank you very much.
Thank you very much. If the gentleman's still here, to have a token of love.
Thank you very much.
If I could ask Kushum Shakya, even swifter on. If I could ask Ranjan Dugal.
Working on reconstruction project at NSET Nepal. Today I'm going to talk about the learnings on reconstructions, around reconstructions for the retrofitting works on masonry building specific to the rural building, that means stone masonry with mud mortar or dry stone masonry things. And for that, learning on implementation of stone masonry. So just I'm going to give a quick flavor of damage of earthquakes, that we do have loss around 7.5 billion US dollar, and half of that stake is to be taken by the building damage. And the current context of reconstruction shows that around 48% rural housing reconstructions has been completed, but only 1% have only retrofitted, among 7% listed as a retrofitting beneficiaries. So building damage, the context is like this, the rural context, just this gives the flavor of rural houses for you. So see, these are maintained after damage. So these are the few houses that we work for retrofitting.
At the same time, it's used also for monitoring. So numeric modeling can combine all this data and can be used for slope stability and depth.
It is very nice presentation, but I'm so sorry for our twice electronic accident. And we couldn't have enough time. So now we'll try to present you.
And if we talk about this,
I'm going to have still time.
Okay. So last point. So if you are doing retrofitting, we are going to save around 181 million Nepalese rupees in order to invest on like all productive sector of building constructions. We can save that if we adopt that technologies.
retrofitting options within the. If we are able to do retrofitting of this 65,000 households that has been listed as a retrofit beneficiaries, we are going to saving a significant number of national cost of national investment. That is what. So these are the few clips.
Yeah, thank you very
if
much.
You have any questions, but yeah. Yeah, so just stop here.
Yeah. Thank you. If I can just say thanks.
Yeah.
I'm sorry, but we're going to have people at tea time walking through here, so I'm just trying to keep.
So if I can ask Regina Pradhan, you're up next, talking about earthquake resistant assessment of building construction technique and, excuse my pronouncement, Niagan settlement of Kavre for the Gorkha earthquake.
And thank you for the organizer and my supervisor, Dr. Prasanna Sudan, for providing me such opportunity to deliver the presentation on the building construction technique assessment in the Niagan settlement before the Gorkha earthquake. These are the outline of my presentation. This includes introduction, literature review, methodology, and result and discussion. Introduction. Nepal is one of the most vulnerable countries to the impact of the after disaster in the world. Nepal has faced in April 2015. In 25 April 2015, Nepal has faced a heavy earthquake of moment magnitude about 7.8. And in this earthquake, nearly 9,000 people have lost their life and nearly 22,000 people become injured. And the epicenter of this earthquake was Gorkha Barpa.
There will be political issues later on if any fatality that happen to the student, because the student is precious. When you are in university, the student is always number one. Yeah. And clearing all large and loose debris on the slope to avoid further rollover of the slope, over the slope, because on top of the hill just now, there are a lot of actual debris. So we have to make sure that the debris get clear and everything will be performed immediately. And all drains and some were cleared from blockages to avoid self-creating streams and transporting loose and weathered material to other locations. That's what you see just now with the car, with the car actually moving and all the debris and all the weathered material, loose and soapy sand and so on are being covered along the road.
I'm Scott, we have no electronic accident, but anyway, we have no time to have a discussion and questionnaire. So please come up to here. Naoaki Suemasa.
I'm Naoaki Suemasa from Tokyo City University in Tokyo, Japan. So I'm very happy to have the opportunity to talk on my work here. So I will explain today about screw drive sounding and screw drive samplers. So this is background. Large earthquakes frequently attack to Japan, so which causes heavy damage, such as landslide or liquefaction, especially in residential area. So liquefaction damage is very severe. However, such situation has not improved at all for a long time. So I think people should know the information of ground who are living on. So to do so, the estimation liquefaction potential is quite necessary, right? So here is a list of tools to estimate expensive. So it is used just for important structures. CPT is not so popular in Japan. So in residential area, Swedish weight sounding and simple sampling are used to estimate liquefaction potential. This is quite cheap, but not so accurate at all. So we revised Swedish weight sounding of testing manner and developed screw drive sounding and screw drive sampling. We developed that. In the test, the rod is always rotated at constant speed. Within the interval of 25 centimeters of penetration, applied load is increased stepwise, like this one. At each load stage, vertical load, applied torque, and settlement rate and the rotation speed are measured and recorded. Okay? After the interval, the rod is lifted up to 2 centimeters and rotated and measure the rod friction. The rod friction is used to deduct the rod friction from the data using these equations. Okay?
With these large landslides, especially in Himalayan environment, like these dynamic chains, they might occur at high altitudes or somewhere in the higher elevation areas, but the thing is that they can have effect up to the downstream. Like when a landslide occurs and it dams a river, there is always a chance of dam burst. And also for snow avalanche or landslides, they can always entrain some material and they can always get bigger when they move, right? And they can also affect huge number of settlements in the runout. So these are common damage. But here I would say some of very catastrophic landslides, like the Vajont landslide. This was in Italy, about 2,000 deaths. More than that, they had the casualties. The thing with this landslide is that there was a big dam that they had constructed, and right before this, there was this huge rock mass that was really unstable, and people knew this is going to fall. And the engineers, they had, because it was already active, and the engineers, they had predicted that this thing is going to fall. And they estimated, okay, this much mass will fall with this much velocity, okay, and then they also lowered the reservoir level. But when the mass actually failed, the tsunami, the wave it generated was way much higher than how much they had expected. And it created massive damage on the downstream. And so when your estimates get wrong, things, such catastrophes, they are unavoidable. And also in case of, this is also a famous avalanche called Husparan avalanche in Peru. And this was actually triggered by an earthquake in the high mountain areas, and then it moved really, really long distance downstream to sweep away everything, engulf everything that came on its path. So these large avalanches are really, they have to be understood. These process chains, they have to be understood. So similar event occurred in Nepal, and the Gorkha earthquake, it provided us an opportunity to actually see such kind of events and calculate. And my case is the Langtang avalanche, and this is the site. I saw only 500 meters, but this site was like about 3 kilometers from crest to toe, and around 5 kilometers in extent. And but this big mass of rock, ice, and debris, it started from this source area with the mountains and with all debris, and when the earthquake triggered, this all mass was mobilized, and then it started to fall, and then from this around 500 meters altitude, it just bumped into to the village, and the village was wiped off. More than 300 people, they were killed, and there were also massive damage in, this is a building, just a part of the building that survived, but all the village it was buried. And there was the avalanche was about 120 seconds, all the mass that came onto the valley floor. And the average velocity, we estimated around 48 meters per second. This was quite high. In comparison to the avalanche in Peru, it was around 30 meters per second, but this was very high, especially because there was this around 500 meter jump that it took. So, and the runout distance was around 5 kilometers. And you can see this is the 5,000 meter contour, and the material above this is the ice, and here in this part it's the rock debris. And so you can actually trace all the sequence of events that actually created this massive destruction. So, and also with you need to calibrate this model not only in terms of the areal extent, but also in terms of the stage in which this process occurs. So people in that village, they had observed, actually it was a number of avalanches. They struck at different times. It was not a single big event. So with this two-phase model, what we can say is that you can see this is the solid, this is the results from when I consider solids and fluids separately, and this is the result when I consider both them as a mixture. And you can see, if we consider solids and fluids separately, you can see 5 different sequences of events that are coming. So it's also creating those events, it's also recreating those events. But if you consider this solid and fluid mixture, it is not able to reproduce what the villagers have witnessed. So, and we can see that when we consider, when we have this two-phase mixture, this model gets more better in predicting stuff. And you can also always get these nice plots of pressures, velocities, and these estimates, so which are always helpful to validate some of the results.
Nice presentations. You told that the average velocity of lifetime avalanche is 48 meters per second.
Yes.
How do you calculate the velocity of avalanche?
Okay. When you run this model, this finite difference scheme, for each pixel, it's based on a raster calculation. For each pixel, you solve the flow. Okay, and in every step, when it starts to flow, and every step, the velocity, if it's a steep, it gets added in the raster. Okay, and for each sequence, for every time step, let's say for every 10 second, 20 second, 30 second, you have a solution of the velocity. And when you sum up and average all the time steps from the number of simulations from, let's say, 0 to 300 seconds, when you average the velocity for all the pixels, then that's how you get the average velocity. I don't know if I got you.
This model needs to work for another avalanche?
Thank you. That's very important question. The thing with these large landslides and avalanches is that we need more data to calibrate these events. Okay, and if the landslide occurs in a similar setting with the glaciated ice debris, and especially in case of Nepal, we have been using a lot of empirical models and the landslides data from Alps and some other mountain ranges. Instead of that, you need your own calibrated geotechnical values. So if the situation scenario is similar, especially in the high altitude range in that valley, the geotechnical parameters are quite close. Instead of using for other mountain ranges in other geoenvironmental setting, these values will be very close and better for the prediction models for in case of our country.
Thank you. I got it.
Next presentation, if I could invite to the floor Nishan Gajuro, presenting on the influence of topographic effects, influence on the topographic effects on dynamic behaviour of hill slope buildings.
Good afternoon, everyone.
I am Nishant Gozvinet. I am from Kathmandu University. I was a student of. This is the topographical amplification variation along the cross section of the considered geometry. As you can see that from going 200 meters to 600 meters, which is actually the base width of the mountain, the amplification factor reaches greater than 1. Which states that the motions are amplified only within the portion of the mountain. Go beyond the point of fundamental frequency. The fundamental frequency for this has been taken as 0.5 Hz, and beyond that frequency, there are cases of de-amplification. Furthermore, the cases of de-amplification. These are the result for PGA variations across the section of hill within 15% of fundamental frequency, because most of the amplification occurred within 15% of the fundamental frequency. Although the PGA value in this particular instance is lower, but the amplification factor is increased in context of frequency of f equals to 0.2 and 0.5 Hz. The conclusion from the study is that amplification is dependent on the base width of the mountain. That means if the wavelength of incoming wave matches the base dimension of a particular hill, then we can expect the resonance of whole relief. So the cause has been attributed to resonance of whole relief, and the frequency range for topographical amplification. Say we are trying to model a particular geometry for topographical to find out the effect of topography, then the frequency range selected within 15% of the fundamental frequency of that hill. The maximum topographical amplification points were observed at crest and slopes.
My name is Martin Said. I'm from Czech Republic, from Czech Geological Survey, and I will present our part of the examples of our Georgian project, Georgian cooperating with the National Environmental Agency. It's a catastrophic debris flow in Kathmandu mountain area, Georgia, and the use of available free internet information for the generation conceptual engineering geological models. For example, we use the area on the border of Georgia and Russia here. Here is a little concept of this presentation, some words about geology, some words about conceptual geological model in general, some examples of debris flow, what we used about the examples in this area, and I will show you the resulting conceptual geological model on this area in terms of debris flow. On the valleys are quaternary moraine and debris, colluvial sediments and alluvial sediments. And on the upper part of the mountains are glacier and fen fields and permafrost. Now I want to say something about the conceptual engineering geological model. I will explore approach of IEG Commission C25 on the use of the engineering geological models. The Commission distinguished two models, conceptual. The relationship between engineering geological units. They are looking at geometry, involve the reliable high degree of uncertainty, and observational approach is based on understanding the observing and measuring distribution of this is our example. What we use. This is our map, inventory map of the historically documented the debris flow on this area. There is a mountain, Kazbegi Mountains with highest peak, Kazbeg and Jimara. It have 5,000 meter average level. Here you can see a distribution of the glacier, and they continue to the valleys. And the red polygons represented the debris flow. First example is Devdoraki Glacier here on this part, and then run out to Dariali Gorges here. Kolka Glacier collapse. This is Kolka Glacier, and the Kolka Glacier caused a big debris flow in Kathmandu Valley, destroyed Kathmandu village. Abana Glacier here on 1910 ran out here, and last example, Mena Glacier. This part, Mena Glacier. For the part of the Devdoraki Glacier, in this part, follow the part is this glacier fall down and cause the debris flow. There is any damage. There were two tragic events in the recent part. In the Dariali Gorges, east of the mountain peak, fall of the part of the Devdoraki Glacier activate debris flow, which blocked Dariali Gorge, and movements were reactivated due to abnormally terrestrial strong rain. And here a scarp area. In the next slide is detail of the scarp area. Here is the satellite image on the figure A from the Google in 3D visualization, and this is a picture or image from the monitoring camera. And it's a drawing of the collapse area. It was 5 million cubic meter.
I really think geotechnical parameters need to be studied in structural engineering as well. As structural engineering itself says that it is interaction between the structure, foundation and its underlying soil. So I have tried to use some soil parameters in my structure building models in order to see how those structures that are modeled with the soil parameters and that are modeled without soil parameters have the responses, and how they are different and how they can be improved in the future as well. The main objective of my thesis is to investigate the overall response of acid-frame buildings, and I have concentrated my work in residential and commercial separately, and to conduct some specific analysis on the building, including the SSI effect, and to evaluate the differences in the effects if it is included and if it is not included.
So this is the outline of my presentation: introduction, location, introduction to the Kathmandu place, material and methods, result, discussion and conclusion. Going to the introduction, activity is the ratio of plastic index to the percentage of plate action. It measures the water holding capacity of the soil. Since it is a key parameter to know about the sinking and swelling properties of clay, and Kathmandu Valley contains most of the pipe, I find this topic very useful and I will research in it. Relative study of the soil consistency is inside the Kathmandu Valley. Analysis of soil activity of Kathmandu Valley to find the relation between adequate limit and water content, and finding the constant value, the 10 beta in the equation, which is developed by Corps of Engineers, US Army, for Kathmandu clay empirically, to study the percent of clay finds in different parts of the valley, to study the consolidation parameter and for the Kathmandu clay, and study about the swelling properties of Kathmandu clay. The materials and chemicals used are listed here. This is a laboratory work, limit test, plastic limit test, specific gravity test, plastic particles distribution, and acidity fraction test, and also reduction test were done in laboratory. The result, first of all, consistency of soil test results are tabulated in the table. The activity ranges from 0.27 to 2.11 with average activity of 1.19.
Profile 2. Pipeline is passing along the road at a distance of 2.5 meters and the depth of 2 meters. And another pipeline also passes along the road at a distance of 8.5 meters from the left flank of road around 1.9 meters depth. There are various pipelines passing across the road at 3 meters, 30 meters, 35 meters, 37 meters at a depth of 1.3 to 2 meters depth. Can be seen in the diagram. This is the parabolic shape. Similarly, pipeline passing on the road at 1.5 meters at a depth of 1.8 meters, and the other is at a distance of 8 meters at a depth of 1.7 meters. And if we go across the road, you can see the pipeline at a distance of 1 meters at a depth of 1.5 meters, 30 meters, 1.8 meters, and at 20 meters at a depth of 1.5 meters. In profile 4, pipelines are running at a distance of 0.5 meters, 1.5 meters, 8.5 meters along the road. If you go across the road, they are distance of 5 meters, 8 meters, 30 meters, 25 meters, 30 meters, 46 meters, at depth of 1.5 to 2 meters. In profile 6, pipelines are running along the road at 0.5 meters, 2.5 meters, 6.5 meters at depth of 1.8 and 9 meters at the depth of 1.8 meters towards Malabans area. Many other pipelines are running across the road at the distance of 0.5 meter, 21 meter, 35 meter, 42 meter, 45 meter across the road at the depth ranging from 0.8 to 1.5 meters. See with the location 7, 5 utilities are running along the road in 0.5 meter, 2.5 meter, 6 meter, 7.5 meter, and 8.5 meter along the road. And 2 utilities are passing across the road in the profile of road 7. Several utilities are passing across the road at a distance of 0.5 meter, 11 meter, 20 meters, 37 meter, 40 meter, and depth of 1.2 to 2 meter. You can see these figures in the parabolic shape. This shows the distance, and this shows the depth of the utilities.
Brought up by the government. So this one is the old Dharra, you can see properly. So the new Dharra is allocated to nearly 20 meters east to the remnant. So this is actually a bigger master plan which is made. This place doesn't look like this right now. It's all scattered and like differentiated from one another. So this is actually a big master plan made by the government, which basically has silty clay, which is black in color. So black clay is Kalimati in Nepali. So it's basically a Nepali name. So this formation is almost 450 meters in depth. So seismic consideration of site. So UNDP has UNDP has given this site as medium to high hazard zone. Also, talking about the lithology, so the shear strength deformation is seen to be possible. Samples was collected by Selmis apparatus. So this is the split film sampler, which I wanted to show. So this is the informative textboard which we usually take photographs with before conducting the test. So this is the split film sampler. We got this disturbed samples by this sampler. So we also conducted the water table monitoring system, which we so the water table was checked at every 24 hours. So these were the number of tests we carried out. Sea analysis, national moisture content, so all these things, consolidation and direct shear test as well. Which these two tests were done with the undisturbed sample by service apparatus, and all these others were carried out by the spirit full samplers.
Suicha Segal from Kaga University. I chair this session. I'm co-chair.
Hello everybody, my name is Jakub Brahar and I'm from Czech Republic.
I'm Suresh Adhikar and I'm the recruiter.
Thank you. This session we will hear 3 invited lectures and 3 technical presentations. Our first invited lecture is implementing the Sendai framework in developing countries using remote sensing technique for the evaluation of natural hazards by Dr. Michael Whitworth. Please.
Thank you, Chairman. Anyway, we all want to have dinner and have lunch, so would I get 2 minutes warning, Chair? We'll be starting this evening session talking about implementing the Sendai framework in developing countries using remote sensing techniques in the evaluation of natural hazards. And what I'm going to be focusing on is the utilisation of GIS information management systems based on open source remotely sensed data. So the contents of my presentation is, first of all, I'll give a brief introduction, firstly of why engineering geology is so important to disaster risk reduction and the key role it plays. What is disaster risk reduction and why is it important for Nepal? But also, due to the fact that I'm talking about open source data, I'm going to talk about the difference between a preliminary or screening assessment versus a detailed assessment. I'll also highlight the data availability. Some people might not be aware of the breadth of data that is available free of charge through a variety of sources. And then I'll run through some examples talking about the urbanisation of Kathmandu and how the development of Kathmandu is really increasing risk. Looking at how you can utilise remote sensing data to do landslide mapping, how you can utilise data to do flood risk assessments, evaluate tectonic activity through the process of nick points, but also more from an engineering geological point of view, look at something called site assessments and also something about detailed assessments. And then, due to the fact that it's open source data, I will talk about some of the limitations. So this is a picture, I think most people are familiar with this. This is the Araniko Highway. So I've been doing field work in Nepal since the 2015 earthquake, working with a variety of institutions, including the University of East Anglia and the University of Plymouth. I myself am from ACOL. So why am I here? Why am I presenting to engineering geologists talking about disaster risk reduction? I'm an engineering geologist by trade. Engineering geology sitting here links to a variety of things. It links to infrastructure, it links to the environment, it links to how we build things, why we build things and where we build things. It's fundamental in our land use planning, and therefore engineering geology is fundamental to evaluating geohazards, evaluating risk, and therefore supporting disaster risk reduction. Just a brief introduction about disaster risk reduction. Many of you are aware of, I'm sure, of the Nepal Disaster Risk Management Act that was enabled this year or last year, and that fundamentally links into 2 different frameworks: the Sendai framework and the United Nations Disaster Resilience Scorecard. So the Sendai framework, its aim is to substantially reduce global disaster by 2030, aiming to lower the average global mortality rates when compared between 2020 and 2030 compared to 15 years previously. Fundamental to that, and its priority 1, is understanding disaster risk. And what I mean by that is to be based on all understanding of disaster risk and its vulnerability and its capacity. The United Nations scorecard is a method for evaluating how resilient a city structure is to natural disasters. And fundamental to that, sorry it's a bit too small, is identifying and understanding current and future risk scenarios. So what I'm really here to talk about is I'm not here to talk about in the Sendai framework there's priority 1, 2, 3, 4, 5, and in the UN scorecard there's actually 10 different aspects. I'm here to talk about disaster, evaluating the natural hazard and how that can be fundamental to reducing risk. So I have to caveat the difference between preliminary screening versus detailed assessments. And this is something you can ask me questions on a little bit later. But the methodology and approach I'm talking about is looking at regional or national scale assessments. The data sets that I'm using aren't necessarily applicable to very detailed site-specific assessments. And partly that's due to cost. All the stuff I'm talking about is freely available, but where you're talking about bespoke data, you're talking about a high cost, both in manpower and also data. So as an example, this is free spot imagery from the USGS, cost me nothing. This is bespoke LiDAR data, cost me £100,000 to fly and process and get someone to do that for me. The difference is, features in this are very difficult to highlight, where in this, even subtle landslide features can be picked up by LiDAR. So what I'm talking about is how you can use data sets like this, free of cost, not in terms of time, but in terms of money, to understand disaster risk. So this was used for a site in the Gulf of Aqaba between Saudi Arabia and Egypt, where we were looking at actually the deep topographic things where there's a massive fault running through here. So we use this actually to evaluate sites. But what's available, all of this data is free. So you can get free digital elevation models from the USGS.
When you scoop a laterite from the top with your excavator, if you take only the top portion, then it's called lateritic soil. If you take only the bottom soil, it's called lithomagic clay. But when in the practice, the excavator will scoop both of them. So in that case, if you have more of the lateritic constituent, less of the lithomagic, it's called lithomagic laterite and lateritic lithomagic. So all this comes under the lateritic soils, but I'll be talking mostly on the pure lithomagic clays. Okay, so the area, as I said, is coastal Karnataka, and it's about 20% above mean sea level, and we get about 3,500 to 4,000 millimeters annual rainfall. There's not much change in temperature, there's no clay. I worked in Bangkok, there is vast stretches of clay, very deep stretches of clay, and they have problem of subsidence because they extract a lot of groundwater, the land sinks, and the sea is adjacent to that. So because of urbanization and rising temperatures, the sea level is rising, land is sinking, sea level is rising. So you know what is, it's a cumulative effect. But in our place, luckily, there is sea level rise, but the land is also rising, right? The rise in land is more than the rise in sea. So we have a net rise in land. I'll tell you why, and that is to do with the geology. So that's my home state of Karnataka, and I come from this coastal area, Mangalore. Those who know, and there is one more state below us, it's another coastal area where our scientists study a lot of laterites. Okay, and ours is rivers. What is happening is this Indian plate, you know about the tectonic moments. The Indian plate is trying to move and it is trying to push the Asian plate. And at that reach, we have the Himalayan mountain ranges. So that is causing a rise in Himalayas, I'm told about 1 centimeter per year. When it is pushing, when this plate is pushing, I have some more pictures maybe. So this land is also rising. right? So this land is rising by about 2 centimeters per year, our sea is rising by 1 centimeter per year, net is the land raises 1 centimeter. But it's not uniform everywhere. In some areas, which we call as a Konkan belt, that is includes Bombay, the sea level rise is more than the land rise. So it's a lowland situation, right? The sea is rising more. But in other parts, the Malabar coast, the Coromandel coast, and Utkal coast, the land is rising more than the sea. So we call it as the coastland of emergence. This is called the coastland of submergence. And we are here somewhere, and so we have this geological tectonic activity, and also because of the weather, we have lateritic rocks. This place, Hampanakatta, is the center of my city where I'm working now. And at about 15 meters depth, we sampled recently, we found all the seashells and all that. That means it is about 3 kilometers from the beach. So that means the sea, some years back, geological years back, the sea was there. Now the sea has gone back, right, because of this net rise in land. As I said, the lateritic formation is having a top hard lateritic crust and then what is called as the lithomargic clay and then the rock. So the lithomargic clays are problematic soils. They are highly erosive and these are used for filling up lands and developing estates. And sometimes you see those are filled up. As I told you, in the monsoon season we get very heavy rainfall, one of the heaviest rainfall areas. And if not properly compacted, you have these cracks. This is a bridge approach, right? So after the monsoon, it has opened up, cracked out. One person can be easily go into that, right? So no proper compaction, and it's on a lowland. And we have a lot of slope failures in lateritic formations. Of course, these slopes are badly designed. They are very steep. It's a canal. But in our country, this land belongs to the forest department. So the forest department and irrigation department, although both are government departments, they don't work together. The forest department will not give the land. So they had to have a very high slope, steep slope. And in lateritic formation, you see this is the darker one is the hard laterite, and this white patch is the lithomargic clay. It's very steep, and they have built a very cosmetic retaining wall. It's not designed. Engineered retaining wall is designed for lateral resistance, for overturning, for bearing. This was just a wall, cosmetic wall. So it had failed, right? And these are also failures of steep slopes in lateritic formations. You can see some persons here, they're just like pygmies, right? So it's very high, 40, 50 meters high, steep slopes. And many times the slopes are very steep and there is very poor drainage control. The soil is already very highly erosive and plus poor drainage. You see the water, there's ponding of water at the top, water is stagnating at the top, is coming up. It's not a good sign, right? Water should not come out to the face of the slope, right? There should be a proper drainage, you should collect the water and send it away. Now, if you don't do that, this won't happen. There's a building, half the building is submerged into the soil. Right? So, this is another, I should say, bad engineering, where a multi-storied complex was being built without any excavation supports in lateritic formation. So you can see this hard lateritic top, but this whitish soil is the lithomargic clay. It doesn't have any, it's very poor. It's like a dispersive soil, which loses strength on wetting. So it has lost strength and you can see a lot of caving in happening, right? So we studied this lithomargic clay, which also increases and even the angle of friction increases. This is almost matching with the compaction curve at OMC peaks, both of the density peaks, the shear strength parameters also peak. And we did some laboratory tests at varying moisture contents. This is at OMC and this is under fully submerged condition. You can see the strength is so low. So when it is submerged, when it is not confined, when it is moist, it has very poor strength. And so the slopes have to be engineered. That means there should be proper slope angle. Slope stability, what we study, right? The various methods, the Swedish circle method or any other method, is we study only the geotechnical part. Right? The soil, we have the driving force, which is the weight to the bed, and the resisting forces of cohesion and friction. It's not just that. We have seepage forces, we have earthquake forces, we have hydrological parameters, the rainfall, and all that, the vegetation, right? So it's both biological and hydrological and geotechnical. So if you combine all that, combined effort, right? Then we can make a better. So we did lot of tests on the lithomagic plates. We did CBR test. Our transportation engineers like CBR test. Geotechnical engineers like more maybe the Traxel test. But both CBR and Traxel results were very poor. Okay. And some places they have used gabions, the Indian Railways and the Konkan Railway, and in some places we have used vetiver grass. Some of you, I think most of you coming from Southeast Asia, Malaysia, vetiver is very commonly used. Okay, vetiver has its roots very 3 meters and it grows, so it's very effective in controlling erosion.
You worked with us during our stay in Nepal. Just after the disaster. And also, his company is helping us to do a research in Texas of the tornado and in Canada. So your companies help us a lot. Thank you very much. No, first of all, I have to say that. And today, I will give my presentation on this disaster, related disaster and gender issues. And so maybe you feel far away from such this issue in your areas. But please open your eyes on the disaster gender issues. My presentation is focusing on the disaster gender. So our country has many big disasters, but after the disaster, some of the gender issue is occurring. But most of the disaster science researchers don't know what's going on, the disaster gender issues. And just more to hearing our presentation. But it's very important to reduction of the disaster risk. The different impact on male and female. How do you think about it? And aiming the gender equality and the local disaster management concept, that is very important things at our society. Because I was a member of the disaster management concept in Saga Prefecture for 5 or 6 years. I retired at university and I moved to this university, and after me, the position was stored down here. Therefore, one member is reduced. Such a on disaster prevention, response and recovery, and reconstruction measures. So it's very related to gender issues. And gender issues such as so look at on your eyes, and this is shelter condition. This is very popular just condition in Japan. This is elementary or secondary schools gymnastic, and just staying, boarding the bed. So we encourage local government and national government, central government to reform shelter condition to be here. This is our idea to reform the conditions of the shelter. This is made by cotton box, but it's very clean and clear to where is who is where and how the conditions. Therefore, this is and this is do you can you see that this is a fence to take a little bit of privacy? That is very important at the shelter life. So related all of the gender issues, especially the Great East Japan earthquake and the other disaster is really not. So most of the government and the local government also, many people do not consider by the gender or age. Just providing such this big floor to you can take some of the place to by yourself or your family. Just providing our space. Such this miserable circumstances, and many baby were suffered from such this environment. It's a very serious problem for us. And so in our society in Japan, so we discussed about the gender issues from the 1995, and we constructed the gender equality basic law was issued 2000. And after that, we are very, only female is very concerning about the gender issue in our society, but most of men don't know and not concerning about gender issues because of the, our society was just shifting the traditional gender roles, man-centered gender roles. And this is related to the after, before and after the disaster prevention and the restructures. I figured out this, female, lack of equal access to the social participation or I have to show you the United Nations Commission on the Status of Women 58th Commission session on 2014. That is a topic of gender equality and the empowerment of women in natural disaster. So, United Nations also very concerned about the gender issues. Yes, this one. You can say that. Gender equality and the empowerment of women in natural disaster. This is a very important to addressing by United Nations. And so I just figured out some of the big issues. Why we are still having gender differences in a disaster and after disaster. We just evaluated this structure and the female participation local disaster management concept. This is very latest data. So we have, our society has 47 prefectures and 100, about 1,700 municipalities. And so I just feel more.
Visualization occurred. This is site, the great. So when we apply the...
And we have 2, 4, 5 presentation, and maybe we allow only about 12 minutes, yeah, compared to the keynote. Okay, for the first paper, it will be myself presenting my colleague, which could not come over. So I'll be presenting the first technical paper. Co-author for this paper. Supposedly the PhD student was supposed to present, so on behalf of my student, I will present this paper. It's called Slope Instability Evaluation using 2D Resistivity Method of Gua Musa Cameron Highland Highway. So as you can see just now when I presented earlier, was using the resistivity, the 2D resistivity, so it is the same principle, so that we are going to manage looking into the slope instability by looking into this resistivity profile. Okay, I will continue with that. Okay, as you can see that this is a problem in Penang, yeah, 2000. Sorry, no, in Penang. This is the Antarabangsa in 2008. And so what happened is that the top one is of course in Penang, the one of the just after the typhoon, and this one is in 2008. Yeah. So slope failure is a very complex phenomenon, and we know that landslide and the instability is due to so many factors. Yeah. One of it, of course, is the triggering factor is water. This is water. Then, due to all those conditions, the slope failure event occurred mostly due to heavy rainfall and due to tropical rainforest climate with relatively high temperature and received rainfall throughout the year. We have 2 monsoons. Yeah? One earlier in somewhere in December to November till January, and then in June, May, June, July. So currently, before I left Kuala Lumpur, it was in Penang, it was raining for 3 days. Again, the same thing happened. Yeah? But the characteristics of subsurface features in slope failure, because we want to see what happened to the subsurface. Okay? So by doing this 2D resistivity, I'm not good at using this thing. Okay, this is where the study area. This is the mainland of Malaysia, not Penang anymore. This is somewhere in the middle between the east and west of Malaysia. There, I think you know about Cameron Highland, where there is a so-called sort of like a place where there's quite a lot of resort, and there's quite a farming agriculture activities run by the people in the highland, where all the flowers, the vegetables, and so on. But this part of the country, I mean the state, this study area, this is where the main range consists of mostly granite with several enclaves of meta-sedimentary rocks, and the main range granite is located in west and of the state of stretching along the western of Kelantan, yeah, going up. So the Kelantan part is on the northern part. So this is where the state of Pahang, Cameron Highland, and adjacent to it is the state of Perak, because we have only 7 states in this part and another 2 states in the other side of the what we call Malaysia. So this is reported by J. Abdul Rahman and Kama in 2001. The distribution of igneous rock in Kelantan is in the west and east of borders. So these are all actually the main range of granite and boundary range of granite. And generally, the late Triassic age, figure 3, it shows this, okay, on the geological map of the study area. So if you were to look at the purple color, it is the acid, what we call intrusive, and these are more on the granitic, yeah, on the geological. So, okay, because of the site condition, so we are doing this 2D resistivity method, and by doing this method, the electrical currents are inserted in the ground, okay, tapped into the ground, and resulting, giving us potential differences, okay. And variation in electrical conductivity of overburden material produce varying value of apparent resistivity. That's why from the 2D profile later on you will look into it, you can see the different color, it will give different ohms, yeah, per meter, different ohm meter. So it will show you what is the range of the resistivity, and there's a correlation between the resistivity and the type of material that electricity can penetrate, yeah, because of the conductivity, yeah. And okay, this is the equipment being used, yeah, by the 2D resistivity method. They are doing the data acquisition with the array. That means they have to have a line, the one that I showed earlier. You have to have a line, and from that line we can do the data analysis with the software, REST-D, and of course we can do the data interpretation by using server. So these are the conditions, yeah, that they are using the Venus converter array, and it is a 2.5 meter minimum electrode spacing every 2.5 in one line. Every 2.5 they will do a hammering to actually pass the electricity, yeah. So with that we can do the process of measuring the conductivity and so on. Then
district overall, and they have completed 85% reconstruction and land development programs, whereas at national level only around 50% completed. This program very much relevant. In case of transparency, the civil society organization organized public auditing and social auditing things that promote, that lead to the transparency and good governance in the study areas. As far as the social mobilization part is concerned, that is very much important aspect, and to mobilize the community in order to aware, organize, and take action at the community levels. They have trained social mobilizers, around 54% male and 46% female social mobilizers. They are doing the social mobilization work in the eastern areas. And good governance is intervention to change the existing practice for the community, people to promote the transparency and downward accountability, because of NGO has much more focus to the community-based program activities, and they have shared all the activities and trained and always organized to the communities in coordination with the government agencies. The gender equality and social inclusion also they had was to focus. They have formulated policy of GSI, and they have practiced the GSI theory into translated into practice. Gender roles of men and women, when farmers can participate in the community, women can participate in the community training meetings, in the other social activities as compared to the previous one. And previously, and they worked on 16 hours per day. Women now, and they work working 15 hours per day. This is 1 hour time is reduced because of social mobilization and gender awareness activities in the community. This is the GSI aspect is a more complicated aspect, because in Nepal the patriarchal social structure is still dominating the society. The male make the decision much more outside the household and the home. Still women are much more engaged in the household than was before. In case of challenges, and there are some challenges also studied or figured out in this study that the landless and ultra-poor families still excluded in the reconstruction liability program. This is the main problem across earthquake affected areas, in case of our district as well. Inadequate field monitoring and evaluation of different stakeholders like government, civil society organization, and donors as well. Inadequate linkage and coordination with the central government and the local government, what is called municipal government. This is also lacking in the different locations, and that happened the smooth running of water schemes in the communities because they have not been constructed timely because of source conflict and in the study areas. This is also a problem. And poor access to loan to a poor and vulnerable family and for the livelihood recovery, because to get the loan and there is a need of title certificate property, that there is poor access to loan for liability activity, inadequate supply of labor in the construction sites, then the huge demand of skilled and unskilled labor for the reconstruction and recovery works. There is lacking and poor management of basic materials, created environmental problems in earthquake affected area as well. This is the problematic areas all over the earthquake affected areas as well. Conclusion and overall program options and the reiterate is that how the poor and vulnerable community should be taken into account and for the reconstruction and land recovery program in the earthquake areas. As far as the recommendation is concerned, the following recommendation has been proposed: the increased coordination and collaboration with rural municipalities and with the reconstruction program. The second one is enhancing the gender equality and social policy practice effectively in the police cycle old management and design private sector adaptation program in the earthquake affected survivors and vulnerable communities as well.
Thank you, sir, for a wonderful presentation. I would agree that we know that the magnitude of the earthquake that differs in the plain region and in the ridge or top of the mountains. Is there different modalities made by the government for the reconstruction of the buildings for the different areas? And what are the challenges and what are the difficulties that the general people are facing in the reconstruction of that areas?
This is a good question. Thank you for asking these questions. Because government have developed 34 prototypes structures in different parts of the countries, particularly focusing to the earthquake affected areas. And the government program is not much more and geographically and focused. And they have a blanket approach, and they have a policy for same policy for the Himalayan, mountain, hills, and foothills or Tarai area as well. This is the problem of government programs. They have blindly designed blanket approach programs across the earthquake affected area. There is a specific and targeted issues, programs, activities in case of mountains, hills, and Tarai. Some civil society organizations have designed this sort of programs, what you have raised, particularly focusing to the Tarai and hills and the mountains, whereas for governments, we did not.
Why Gorka has got 85% and you feel that nationally it's 50%? Why the difference?
In case of Gorka district, there are a lot of civil society organizations, national and international organizations are focusing much more program in the Gorka district, because Gorka district is the epicenter of the earthquake as always. That is why the government also much more focused, and NRA also focused in the Gorka districts, and they have supported and for the settlement to construct the shelter in different earthquake area in Barpar and Laprak as well. This is why the Gorka district has made progress higher as compared to the national level. But in case of national levels, because frequent change of governments and leadership of the NRA and timely late decision-making process, and they have not done properly in other areas. But in the case of Gorkhas, there is much more progress as compared to the national areas.
Thank you. I have to keep time. We go to the next session. Thank you. Just a moment.
Thank you.
Degradable mats, it can be the polymeric mats as well, based on the slope, angle and geometry. These are the special erosion control measures, hydraulically applied erosion control measures. We are improving the soil property by doing this agronomical test and adding the biotic soil media. I just quickly run through the case studies. This is one of the projects in Arunachal Pradesh. Landslide problem. This is the destabilizing forces. We have done the seismic reflection geophysical investigation based on which the parameters were selected. This is the slide analysis file. We have provided the solution reinforced soil wall in addition to nailing with the given wall at the top. This is a typical cross section. Some photographs of insulation. This is the erosion control measures. You can see the already vegetation is coming up.
Evolution history of Krishnabir landslide.
Landslide disaster of Krishnabir has been famous for the dreadful consequences. The huge landslides in this region leads to serious socio-eco and the environmental disorder near their region. In addition to the fever, geological, blasting and building activities, rampant deforestation, heavy monsoon rain, and the poor drainage are the indicator for the weakening the natural slope, resulting in the perpetual slope failure of Krishnabir. Stratigraphically, this area is situated in the upper Nagod group of Nagod complex at Bengal formation. Bengal state stocking and water 1980, which is one of the major formation of upper Nagod group, predominantly at the Krishnabir area. Geologically, this area has alternate rates of high axophyllite slates and the carbonaceous slates at the upper middle part of the slide area. The major failure occurred on August 11,000 when they used mass between the two slide heads. The failure was so massive that it demands the border of the river for a short period of time. Heavy rainfall from the early monsoon of year 2000 during the frequent slope failure at the east and west part of the slides, and the locations of mine area. Krishnabir is located 83 km west from the capital city of the Kathmandu in Darjeeling district, which lies along the Kiri highway area. Falls on the topographic area in the map number Sahara. Geologically, this site lies in the west Himalayan and central Nepal. On the northern side, along with surrounded by the MCT and the MBG on the southern sides. Main objectives of my research is to evaluate the evaluation of the Krishnabir landslides, evaluation of Krishnabir landslide cause and mechanism of Krishnabir landslide. To calculate the factor of safety and determine the present slope stability condition. Materials and software used during the entire circle, topographical and geological map, GM and digital geological compass, MR, GPS, measuring depths, mover, RGS, geospatial layer, sign up initial flow failure in Krishnabir landslides, and failure prior to the August 11,000 failure on May 24th, 2000, when the road was closed for about 15 hours. But since then the road was closed 18 times, closing the road more than 160 hours. In mid-August, failure on August again. The failure also mentioned that the damage and thundering the tissue river for a short period of time appeared for and occurring the slow failure in the parts. The stability scenario after the August 11,000, the minor drilling to where the caused the road blocks for the hours and mid-August 2000 to 2001. The failure becomes the more complex in terms of their failure models and mechanical activity of event on 11,000 hours. And this is the photographs taken by the nurse Sake and 2000, and this is the video remaining on the top and after the slice 2000s, and in 2006 the bioengineering is done to mitigate the unstable distance slopes. This is the figure after the bioengineering 1 month plantation, and this is the after the plantation of slope at thousands, and after plantation of 2005, and this is the 7, and this is the same photographs on August 2018, where the main vegetation is overall covered and slope seems to be stable. And this is kinematic analysis. I have done some measures over here, and this is the topping failure in illustrated the slope of this system to depend, and the slope seems to be in opposite directions. And where the waste failure in these arms and nice sides, and this is the topping failure, which is high percentage of topping failure, and this stability analysis maybe. The slope stability analysis was found out with the geoslope down to low and studio 2000, and factors of the less that was compared with the long-standing pricing methods. And this is the result of stability distributed landslide stack case. This is where the factor of is 1.06, 1.603, and this is the hydrostatic case where the water tables under table, and this is to be failure, and seems to be a high static is to be stable, and in the seismic case it seems to be failure from where is to where it is factor is 0.08 and 95, and result of stability extremely landing setting in 0.053 gas, the factor of safety is 0.72. It seems to be the failure.
Relief distribution was quite fast. So was there, during your study, was there, did you find that, was there any contingency plans of district or district level? Because we had faced disaster, earthquake in 2015. So a lot of INGOs and NGOs were working in disaster. So was there any contingency plans from the government side related to this disaster?
Yeah, that's a very sensitive question. And yes, of course, like as you said, we have faced so many disasters. These disasters are occurring every year, but like these are drawback, bad luck, like what said, at lower level the preparedness is not that strong. You know, like the local representative was just elected, and the bureaucracy and the civil servant, you know, like because of their incompetency, what I call that, because of the less of the knowledge, like the preparedness is lacking there. So like hardly we can get a main plan, and if you do not have a main plan, like how can we expect for the contingency? So that is the scenario. Did you get that?
Okay, thank you.
With the next presentation.
Thank you, sir.
Thank you. Next presentation will present Prosila Pohrel.
I'm here on behalf of Mr. Vikas Adhikari sir to present our work where we assess the regular variation in the land use and land cover pattern of Kathmandu and also created a flood hazard map. So jumping right into it, we decided to assess the land use and land cover of that area by creating land use maps representing 4 decades from 1989 to 2017, along with that, we decided to see the changes in river dynamics, especially the seismicity of the river, that is how much the river course has stagnated throughout the years. And also we decided to create a flood hazard map for that area. So our study area was Madi, which is a small municipality in Chitwan. It covers an area of about 219 kilometers squares, and it is surrounded by the forest of Chitwan National Park in the north, and below the border is the forest of Valmiki National Park of India. So why Madi? Why did we choose Madi for our study? First of all, it lies in Chile and is a part of buffer zone of Chitwan National Park. And also it has been used a couple of times because of the flood events happening in that area. And luckily enough for us, not much work had been done in that subject. Also, Geological, which is a river draining Madi, seems to change its course rigorously throughout the years. River dynamics of Geological, and also to create the flood hazard map. So the parameters we assess for each of the subject matters are these. So for land use and land cover change, we downloaded satellite images from HGS site, and then classified them under 5 feature classes, meaning water, body, floodplain, because floodplain was really prominent in that area, forest, cultivated land, and bare land. And for river dynamics, we simply calculated the seismicity of the river. We took an extent of 23 kilometers of the river and then calculated the seismicity in ArcGIS. For flood hazard assessment, we considered 4 factors: slope, distance away from the river, that is the proximity, and land use, land cover, and rainfall distribution. We further divided these factors into their subclasses and gave them a value according to the degree of effect they had on their respective factors. So then to create a flood hazard map, we assigned a value, a weight, a rank to each of the factors depending on how much effect they have on formation of flood, giving slope the highest ranking and rainfall distribution the lowest. So our results came out to be like this. So these are the maps we created for each of the decades from 1989 to 2017. We can see changes in these areas and also in the river course as well. So here is a graph showing the changes. So we can see bare land and cultivated land are inversely proportional. That is, most of the bare land decreasing as was eventually converted into cultivated land. And we can see some fluctuations in water and floodplain. These are mainly because the images we considered for our land use classification were not of the same month. That's why. And here the forest, we see it declining, but I don't think this number is an alarming rate considering the time frame of the map we assessed. Also because it could be because lying in the buffer zone of Chitwan National Park, being a part of Tarai art landscape, because different acts rules, regulations were imposed on that area. So you can see cultivated land has increased significantly among other features. So these are the river banks. This is the right bank, and this part here shows the main terrain, which had eventually been problems.
Based on where landslides have occurred, what geology they've occurred in, what slope aspects, and what elevation. So, despite the differences in spatial resolution, you can see that there's a significant change from this area, and then as you head east and higher up, the susceptibility or the potential hazard reduces. So we did run through this to see whether it was statistically valid, and we found that the basic models came out at about 0.61, and the more accurate models with the highest being 0.79. The perfect results were
your data fits perfectly to this line is a value of 1. So actually, the result is different to usual landslide control. So this potentially, we think that this hypothesis is due to permafrost strengthening. But the problem that this leads to, with Nepal being number 4 at risk due to climate change, and the fact that potentially across the Himalayas permafrost extents are decreasing, therefore you're potentially going to be getting increased landsliding within these high things going into the future. Any questions? Well, co-seismic predominantly are basically sharp breaks in slope. They're generally shallower failures within rock. So we've done quite a lot of mapping in different things, so it's quite basically the typology and the morphology of the slope dictates whether it's monsoon or earthquake induced. So typically monsoon are lower elevations and more triggered by rainfall, so they're much more related to superficial deposits. So it's just through geological mapping of the features.
The last presenter, Tejas Kumar, 32 minutes, yeah, 6:32. Okay, with that, I would like to conclude for the third session, and we'll thank all the presenters in our usual manner.
Here, Dr. Ranjan is already here, so I would like to call Dr. Ranjan Dahal to give a token of love to our session chair, Professor Fauzi Ahmed.
You will not be happy for it, yeah.
Important in my room.
Yes.
Okay, one.
This, we would like to conclude this session, and then we are now free.
Yeah, for 10 minutes.
Yeah, for about 10 minutes to arrange all these halls, and then we will again come back and celebrate reception and some other programs.
And India, will please visit the exhibition. Still we have exhibition here. Okay, thank you very much.
Okay, thank you very much.
But it is very important to decide the key parameters in advance so that the important things that you need to ask to the inspector doesn't get missed out. So we based these suggestions based on our experience from the SESP program that started back in 1997. And the SAFE program also includes a geotechnical investigation aspect where a cone penetration test is conducted to develop a geological structure and main-shock after-shock model. It also aims to develop a harmonized geodatabase of the Kathmandu basin, and it also aims to develop a geostudy map for Kathmandu. And these are the 10 CPT sites of the geotechnical investigation portal. So a lot of these sites are centered around the mid portion of the Kathmandu Valley, and 2 are up. One of them is up north, and one of them is a bit down south here. So because it is very easy to forget how uncommon these stone masonry or low-strength masonry structures are in the world. Because the advanced nations have already stopped building low-strength masonry structures, and research on low-strength masonry is scarce in the global context. So it is up to us to initiate this kind of research, and we have nobody else but look to us to further this kind of research. So along the link from DFID, so the lab used was from the Kundig University. So we conducted some in-plane shear tests, in-plane lateral load tests of different kinds of stone masonry walls, where we used different kinds of stones from rubble masonry to dressed stones, and we also tried different kinds of retrofitting techniques to see how they differ in nature in enhancing both the lateral deformation capacity and also the strength of the walls. And we also performed some 3D model tests, as already mentioned by Ranjan sir in the previous session. So we built 3 3D models of 2-story buildings. These are typical Nepali houses, and one of them was unretrofitted. The second one here was provided with seismic enhancements of seismic bands and posts, as mentioned in the IPC code. And the third one was, in addition to the seismic bands, it was provided with the GI wire meshing throughout the building in and out. So the result was
extremely good that even surprised a lot of experts. Even at 1 G of excitation of the El Centro earthquake, the building not only didn't suffer a global collapse, it didn't even suffer a substantial local failure in any of its walls. So this was a very good result that was exhibited. But we always had the question of whether or not we should do a local test, because this building was built using very well-cut stones, as you can see here, and it was built using very skilled manpower in the laboratory. So we always had it in the back of our mind that we should do a local test using our local materials, local labor, and local technology. So we devised a lateral pushover test of stone masonry walls. There were two models basically. So this one is unretrofitted, and this one is retrofitted. So it was an out-of-plane monotonic lateral pushover test, and the objective was to observe and quantify the effectiveness of welded wire meshing in retrofitting stone masonry walls of Nepalese schools. So again, it was very important to choose the local labor. So we brought in masons that had hands-on experience of building these kind of walls, which had built their own houses, their neighbors' houses with their own hands. So we brought in, we hired people from the Kathmandu district that we located from in the Kathmandu Valley, because it is very difficult to find masons who have experience in stone and mud masonry. And the second thing was we chose stones from the Nuwakot district, because it is one of the implementation districts from the Geological program at NSEN. So we had a lot of contacts with the quarries, and we chose the quarries that were very popular, and we did because we knew the ins and outs of the transportation as well. And the third thing is we use welded wire meshing for retrofitting. You can see two vertical splints here on either side of the wall, and three horizontal bands, one at the bottom, one at the top, and one in the middle. And the load was applied using a hydraulic jack at 2/3 height of the wall to simulate an earthquake loading like we do in a normal pushover analysis. So it was, and we devised some accessories in the Institute of Engineering heavy lab so that the jack could be fitted 2/3 of the height. These are just some pictures showing it. And most importantly, although we have to use the local masons experienced in stone masonry wall building, we have to ensure that the people responsible for retrofitting those walls are trained and experienced professionals that are supervised by qualified engineers. So we hired people that were experienced in these works, and we also brought in an engineer from our Geological program from the Nuwakot district who had previously supervised this kind of work in the field as well. So this was the final form of the welding. And talking about the result, you can see on the left, this is the final deflection of the unretrofitted wall before failure. And in the middle, this is the final deflection of the retrofitted wall before failure. This kind of looks like I did a very bad job at cropping this picture, but the reality is the deflection was so big, the deformation was actually more than 2.5 feet. So this wall actually went behind this partition wall of the laboratory that we're testing in. So as you can see from the numbers, the top deflection exceeded 250%. So the top deflection, the deformability at least, was enhanced by more than 2.5 times from that of the unretrofitted wall. And as for the maximum strength, the maximum load capacity, it was enhanced by 85%. Now, you cannot see the exact numbers here because we have yet to exactly calibrate the numbers that we obtained from the analog hydraulic jack. So we are now going to calibrate it using a digital load cell, so we are in the process of it. From these numbers you can see that both the strength, the load bearing capacity of the wall, and also the deformability is highly enhanced by using this kind of retrofitting techniques, by just simply using the available welded wire meshing, and also Gaussian wire meshing in the rest of the part where the welded wire meshing was not used.
The technical session. Thank you for attention, and thanks to all presenters for nice presentations.
Dr. Suman Manandar in the stage.
I'm already here.
Present token of love to Professor Suichi Hasegawa.
this session, we would like to conclude today's session. So now maybe we are very much tired, and then it's time for reception. So after 5 minutes, reception ceremony will be start. So be free, and then again come back after 5 minutes. And then we have some other programs to enjoy together. Thank you very much.